Hello fellow sapiens, and welcome to Sleepless Homo. Take a moment to quiet your mind, whether you're settling into bed, easing through work, or simply letting a slow story carry you. Here we explore science softly, not wild speculation, but humble attempts to understand the past, knowing the answers are never complete. If you enjoy this kind of long-form storytelling, consider liking and subscribing. It helps others find their way to knowledge, and maybe conquer the world with a little more calmness and curiosity. I'd love to know when you listen. Do you use this while drifting off, driving, cooking, showering, or working with headphones? Or perhaps share the time and place you're watching from. And if you happen to fall asleep halfway, I've placed timestamps in the description so you can return the next day, because this whole story is worth hearing, beginning to end. And as always, stay curious, stay calm. Now, let's step into the Cenozoic Era, the 66 million years when mammals rose to inherit a dinosaur's world. 66 million years ago, the world changed in a matter of hours. A rock from the sky, perhaps 10 kilometers across, plunged into the shallow seas of what is now the Yucatan Peninsula. The impact released more energy than all the nuclear weapons on Earth combined. It was the moment that ended the reign of the non-avian dinosaurs. Yet the story that concerns us here is not only about the thunder of the blast, but the silence that followed. What did Earth look like the day after? What did life feel like when the mighty had fallen and only the shadows stirred? The first thing to imagine is darkness. The asteroid punched a hole in the crust, vaporizing rock and ocean into a towering plume. Tiny glassy spherules rained down across the planet, heating the atmosphere enough to ignite forests on continents thousands of kilometers away. As the fires died, smoke and dust and soot gathered into the stratosphere. The sun dimmed. The surface of Earth cooled rapidly. In the days after the impact, the world was a place of night without stars, a twilight that clung for months and even years. In this shrouded world, food chains snapped. Plants could not photosynthesize under a darkened sky. In a matter of weeks, the forests and plains that had fed the great herbivorous dinosaurs withered. With them went the carnivores who depended on their flesh. Even the ocean suffered, as the plankton that powered marine ecosystems crashed in abundance. For large animals, survival was almost impossible. The mighty bodies of hadrosaurs, ceratopsians, tyrannosaurs and mosasaurs were engines designed for abundance. They needed a constant flood of calories. In a world of famine, their size became a curse, and yet, in burrows, hollows and leaf litter, the smallest creatures persisted. Among them were the early mammals. Most were no larger than rats, with generalized teeth that could process insects, seeds, roots, and almost anything edible. Their small size meant lower energy demands. Their flexible diets meant they could switch from berries to beetles, from grubs to green shoots, depending on what was available. Some probably raided carcasses, scraping nourishment from the fallen giants. Others may have survived by hibernating or lowering their metabolic needs, waiting for the worst to pass. One of the paradoxes of this moment is that survival did not necessarily reward strength, but modesty. It was not the apex hunters that endured. It was those who lived in the margins, able to exploit scraps of ecological space. Fossil evidence from North America shows that many lineages of mammals were struck down just as harshly as dinosaurs, but a few clung on. Paleontologists have traced tiny teeth in ancient sediments, the kind of evidence that only a microscope can reveal. These teeth tell us which species crossed the boundary between the Cretaceous and the Paleogene. The line is razor thin, yet it represents the difference between extinction and continuity. The skies of this world were likely empty of birdsong. Many bird groups vanished entirely, particularly those dependent on forests that no longer existed. Only a handful of lineages survived, ancestors of today's waterfowl and ground-dwelling birds. The silence would have been broken by the crackle of fire, the collapse of trees, and perhaps the scuttling of survivors foraging in the gloom. It is hard for us to imagine such a landscape because our own world is so full of life and light. Yet Earth in those days must have seemed like an alien planet, familiar in shape but stripped of its abundance. The oceans too were transformed. The plankton collapse rippled upward. Ammonites, already vulnerable, disappeared entirely. Large marine reptiles followed them into oblivion. Sharks and smaller fish, however, endured. The fossil record shows a sharp drop in diversity at the boundary, then the slow beginnings of recovery. The seas grew murky with debris. For those who survived, it was a time of hunger and reduced competition. In the sediments laid down after the impact, geologists find a thin layer enriched in iridium, a rare element more common in asteroids than in Earth's crust. Within that clay layer are tiny spherules, shocked quartz grains, and soot particles. It is a global fingerprint, discovered first in Italy and later matched around the world. It is the signature of catastrophe. For decades, scientists debated whether the impact was truly the cause of the mass extinction. Today the consensus is strong. The asteroid played the central role, though massive volcanic eruptions in India may have worsened the crisis. What matters for our story is that the result was the same. The age of reptiles ended and something else began. What is striking is that the survivors did not step immediately into a world of opportunity. For years, perhaps for decades, Earth remained unstable. Vegetation struggled to return. Temperatures fluctuated. Acid rain fell from the sky. Fire stripped landscapes bare. For mammals huddling in burrows, the victory was survival itself, not prosperity. Fossil pollen shows that ferns often became the first plants to recolonize burned and barren soils, forming what are called fern spikes in the record. These fern-dominated landscapes may have persisted for centuries before forests re-established themselves. Imagine a world of endless low greenery, with little shade and fewer fruits or seeds. It was not a paradise, but a holding pattern, and so the mammals waited. They clung to their hidden lives, feeding on insects and roots, staying small because smallness was safety. In those years, there was no sign of what would come. No one looking into the eyes of a shrew-sized creature darting through the ferns would have predicted elephants, whales, or humans. Yet the quiet persistence of these tiny creatures held within it the possibility of all that followed. Here is where the humility of science matters. We cannot know every detail of those first days and years after the impact. We reconstruct them from fragments. A layer of iridium, a sudden change in pollen grains, the absence of dinosaur bones above a certain horizon. We imagine firestorms and darkness not because we witnessed them, but because the chemistry and physics make them inevitable. Even now, scientists refine the models. Was the darkness absolute or partial? Did it last months or years? How cold did Earth become? These questions remain open, but the broad outline is clear. A blow from the sky ended one world and gave another a chance to begin. There is a haunting quality to this silence. Imagine being there, a small mammal emerging at dusk from a burrow, sniffing the air heavy with ash. The giants are gone. The forests are gone. The air is cooler, dimmer, stranger. You do not know that your lineage will one day inherit the planet. You only know that tonight you must find something to eat, avoid being eaten, and survive until tomorrow. That modest goal, repeated for generations, was enough. What is survival, after all, but persistence through the dark until the light returns? The Age of Mammals did not begin in triumph, but in silence. It began with survivors picking through ruins, with shadows moving quietly under ferns with patience, and in that patience lay the seeds of a new age. And so we ask, if the future of Earth could hinge on creatures so small, in a world so broken, what hidden strengths are we overlooking in our own? In the first few years after the impact, the world belonged not to giants, but to survivors in the undergrowth. The forests that had once shaded the Cretaceous landscape were reduced to charcoal and ash. Across continents, the first green to return came not from towering trees but from ferns. Their spores spread quickly in burned and barren soils, producing landscapes that must have looked like endless carpets of waist-high foliage. This fern spike appears again and again in the fossil record as the signature of ecological reset. It was in these jungles of ferns, humid but low to the ground, that the mammals endured their most fragile age. Who exactly were these creatures clinging to survival? They were not the proud prototypes of lions, elephants, or whales. Instead, they were unremarkable in appearance, no bigger than modern rats or shrews. Yet these small beings carried inside them the blueprint for everything that would follow. Paleontologists call them the disaster fauna of the early Paleocene. That phrase may sound dramatic, but it is simply the label for species that thrive in the immediate aftermath of a catastrophe, filling spaces left vacant by extinction. The key to their persistence was flexibility. Most of the mammals who crossed the boundary into the Paleocene were placentals, marsupials, and a strange lineage known as multituberculates. They were not majestic to look at, but their teeth reveal a story of resilience. Multituberculates, sometimes nicknamed the rodents of the Mesozoic, had rows of cusps on their molars that could grind a wide range of foods. Some had blade-like premolars for shearing plants or insects. In a world without certainty, such versatility was a lifeline. Placentals and marsupials, though less specialized, had the advantage of reproductive strategies that allowed them to populate quickly when conditions improved. Imagine a landscape 2 years after the asteroid. The skies are still dim, though the soot has begun to thin. Ferns dominate, but scattered shrubs return. In the leaf litter, tiny mammals skitter at dusk, their senses tuned for survival. Fossils from North America show that mammals like the archaic placental genus Protungulatum were already present within 100,000 years of the impact. Protungulatum was no larger than a house cat, yet it represents one of the earliest known placentals of the Paleocene. Its teeth suggest an omnivorous diet, picking at both insects and plants. Marsupials were also part of this early caste. In South America, small opossum-like creatures endured. They had survived before by living in marginal habitats, and now those same qualities gave them a chance. Their young, born at an early stage, could be nurtured in pouches during uncertain times. This reproductive mode did not make them invulnerable, but it allowed rapid response to changing conditions. In the north, marsupials fared worse. They would all but vanish from North America, only to return millions of years later. The multituberculates deserve a longer pause here, because they illustrate both the strengths and the limits of early mammal survival. First appearing in the Jurassic, these animals had already weathered multiple global shifts. Their name refers to the multiple cusps, or tubercles, on their teeth. They range from mouse-sized tree dwellers to beaver-sized plant eaters. After the asteroid, they carried on almost as if nothing had changed. Fossils of genera like Taeniolabis show that some even expanded in size during the Paleocene, feeding on the tough vegetation that spread through the recovering forests. They were not ancestors of modern rodents, but they occupied similar ecological roles. Why size mattered so much becomes clear when we compare these survivors with those who perished. Large herbivores required abundant plant life to sustain themselves. With photosynthesis interrupted, they had no reserves to draw upon. By contrast, a mammal the size of a rat could live on seeds stored underground, insects thriving in rotting wood, or even fungi. Generalists triumphed where specialists fell. A paleontologist sifting through tiny mammal teeth in a Paleocene deposit is really tracing a record of ecological modesty. Smallness was not weakness. It was insurance. We should not imagine this world as an easy one for mammals. Even the survivors were under stress. Fossil evidence suggests that mammalian diversity actually dropped sharply across the boundary. Many lineages that had thrived in the Cretaceous vanished without descendants. The survivors were often the most nondescript, indistinct creatures. For scientists, this makes reconstruction difficult. Teeth and jaw fragments are often all that remains. A handful of millimeters can represent the history of an entire species. In this way, we are reminded that paleontology is built on fragments, and our reconstructions are tentative. We know enough to see patterns, but the details of daily life are inevitably lost. Yet those patterns are powerful. The fern-dominated landscapes, the tiny scavengers, the gradual reappearance of flowering plants and insects, the first signs of mammals taking small steps into niches that dinosaurs once held. It was not a revolution, not yet. It was the persistence of shadows in the ferns. Each night these survivors foraged quietly, leaving faint traces in the soil and fossil record. Without them, the Age of Mammals would never have happened. One haunting image comes from imagining multituberculates gnawing at charred vegetation beside the bones of dinosaurs. They were not competitors of tyrannosaurs. They were the clean-up crew. Their teeth could shear through stems, crack seeds, and nibble carcass scraps. Their lifestyle was hardly glamorous, but it was sustainable in a landscape stripped of grandeur. Marsupials, with their flexible reproduction, may have used fallen logs and burrows to shelter their vulnerable young. Placentals, with slightly longer gestation, invested in fewer but more developed offspring. Each strategy had strengths and weaknesses. Together, they formed a patchwork of survival tactics that carried the lineage forward. This was not yet the Age of Mammals. It was the twilight after apocalypse. The survivors had no idea of the legacy they carried. They were not rising to dominance. They were simply enduring, day by day, in a world that had been reset. The silence left by the dinosaurs was not immediately filled. It echoed for centuries. Ferns reclaimed the land before trees returned. Mammals remained mostly in the margins, nocturnal and cautious. The great radiations of later epochs were still unimaginable. As we reflect on this period, it is worth admitting our limits. We cannot reconstruct every interaction. We do not know exactly how long the skies remained dark, or how many generations of mammals passed before stability returned. We don't know which burrower first poked its head above ground and sniffed the air of a recovering world. But we know enough to say this. Survival was possible because of traits we often overlook: small size, generalist diets, reproductive flexibility. These are not qualities that inspire awe at first glance, but they prove decisive in one of the most extreme tests life has ever faced. The mammals that scurried in the ferns 66 million years ago were neither heroes nor conquerors. They were simply survivors at the edge of catastrophe. Yet without them, we would not be here to tell this story. And so we are left with a question that lingers like a shadow. How often in Earth's history has the future been carried forward, not by the mighty, but by the modest? In the first few million years after the asteroid, once the immediate shockwaves of darkness and famine began to ease, Earth slipped into a strange and lush equilibrium. It was a greenhouse world, one where the poles were not blanketed by ice, and where forests stretched into latitudes we would now call subarctic. The climate so soon after catastrophe was almost paradoxically warm. By 65 million years ago, global temperatures stabilised at levels far higher than those familiar to us, and the planet became a cradle for ecological experiments unlike anything before. The question is, how did this hothouse Earth shape the first true explorations of mammalian life? Evidence comes to us in indirect but compelling forms. Geological cores drilled from ancient seabeds contain layers of carbonate shells from microorganisms. Within those shells are isotopic signatures, particularly of oxygen, that record ancient ocean temperatures. These chemical archives suggest that tropical seas reached warmth beyond anything modern corals could tolerate. Even at high latitudes, where one might expect ice and tundra, fossilised wood and pollen grains tell us of swamp forests, broadleaf trees and fern thickets. In parts of what is now the Arctic Circle, dawn light filtered through stands of Metasequoia, a redwood relative. Crocodilians and turtles swam in rivers where winter now brings months of darkness. Such data remind us that our intuitive picture of ice at the poles is a very recent chapter, not the norm of Earth's deep history. This global warmth carried consequences for mammals, who were only beginning to diversify from their shadowy roots. In a world without freezing winters, small-bodied animals could thrive at far higher latitudes than today. Fossils of Paleocene mammals have been found in places like Ellesmere Island in Canada, at latitudes that would seem improbable for their survival if the climates were cold. These animals lived under months of seasonal darkness, but they did so without the stress of low temperatures. Their very presence suggests that mammalian physiology, already somewhat insulated by fur and endothermy, found advantage in a planet where heat was not limiting. Forests that blanketed much of the continents offered both refuge and opportunity. Dense canopy allowed insect populations to rebound rapidly after the extinction, and mammals with omnivorous teeth took advantage of this resource. Seeds, fruits and nuts also proliferated with the Angiosperm Revolution, though the full spread of grasses still lay far in the future. In this warm greenhouse, the mammals had no need to contend with barren winters. They could experiment with arboreal habits, semi-aquatic lifestyles, and ground-dwelling strategies without the risk of seasonal starvation. The world was one vast hothouse laboratory, and mammals were among its most active participants. It is important, though, to resist imagining this time as idyllic. High temperatures came with frequent storms, fluctuating sea levels, and coastlines reshaped by shifting waters. The continents were still in motion. The Atlantic Ocean continued to widen as South America and Africa pulled farther apart, and India was racing northward toward Asia. These tectonic shifts altered ocean circulation, which in turn influenced rainfall patterns. Vast stretches of land were humid rainforests, but others were drier scrublands. For mammals, this patchwork meant that different groups faced different evolutionary pressures. Some remained generalized insect eaters in the shadows of trees, while others took tentative steps into open country. Crocodilians, turtles, and other reptiles thrived in this warmth alongside mammals. Their survival reminds us that this was not simply the age of mammals emerging in isolation. It was a complex tapestry in which old lineages still held ground. What the mammals had, however, was speed of reproduction and metabolic endurance. In climates that did not punish them with cold, they could extend their ranges widely. This may explain why fossils of early placentals appear in such varied environments. The warmth leveled the playing field, giving small creatures an ecological passport to regions they might otherwise have never entered. One of the most intriguing consequences of the greenhouse Earth was the uniformity of its forests. From North America to Europe, from Asia to polar regions, similar plant assemblages dominated. Fossil pollen studies reveal forests that were almost cosmopolitan in nature, dominated by flowering plants, palms and broadleaf trees. This global greenness gave mammals a relatively consistent environment wherever they travelled. Unlike later epochs where deserts, tundra and grasslands fractured the continents into stark biomes, the early Paleocene was relatively uniform. For small mammals, this meant less need to specialise. They could thrive in many places with similar strategies. In this sense, the warmth of the Earth slowed down the urgency of competition. It created a stage of abundance before the more dramatic challenges of cooling and seasonality would arrive later in the Cenozoic. Yet there is a haunting question here. Did the very uniformity of this world delay mammalian innovation? When resources are easy, there is less pressure to evolve novel solutions. Perhaps this explains why, for several million years after the extinction, mammals remained mostly small, generalized, and conservative in body plan. They scurried, climbed, and burrowed, but they did not yet seize the mantle of gigantism. They did not yet take over apex predator roles. The warmth provided safety, but safety can sometimes be a cage. The fossil record hints at gradual shifts during these 5 million years. In South America, marsupials diversified into small carnivorous niches, exploiting the insect and small vertebrate abundance in the warm forests. In North America and Europe, multituberculates expanded into rodent-like browsers. Early placentals experimented cautiously with larger sizes, but rarely exceeded the mass of a small dog. These were subtle steps, not revolutions. The warmth cradled life, but it also kept it in a kind of suspended adolescence. This period also highlights the interplay between climate and geography. Imagine a world map 63 million years ago. The continents are drifting, but connections still exist. North America and Europe are closer than today, with intermittent land bridges across the North Atlantic. Asia and North America are linked through what will one day be Beringia. These connections, combined with the warm climate, allowed mammals to disperse widely. Fossils of similar lineages appear on multiple continents, suggesting interchange. The greenhouse Earth was not just a climate state. It was a world of relative connectivity. Still, our knowledge is partial. We rely on scattered fossil sites, each offering only a snapshot. Sites like the Hell Creek Formation in North America, which records the very end of the Cretaceous and the beginning of the Paleocene, or the Menat deposits in France, with exquisitely preserved plants and insects, serve as windows into these lost worlds. From them, we piece together the story of climates so warm that crocodiles basked at high latitudes, and mammals thrived in regions that would later be locked in ice. But these are incomplete portraits. We cannot yet reconstruct every rainfall or every seasonal rhythm. We speak in broad strokes, humbly acknowledging the gaps. The resolution to this chapter of Earth's story is not a climax, but a foreshadowing. The warmth that blanketed the planet from 65 to 60 million years ago was stable enough to nurture recovery, but it also set the stage for instability. Carbon levels in the atmosphere were already high. Ocean currents were shifting as continents drifted. Within a few million years, the climate would jolt again. triggering one of the most dramatic warming events of the Cenozoic. For now, though, the world remained green and lush, the tropics effectively ruling every latitude. The question that lingers is whether mammals owe their eventual success more to catastrophe or to comfort. Did they rise because disaster cleared the way, or because greenhouse abundance allowed them to persist long enough to try? We may never know for certain, but the story of those 5 million years suggests that survival can mean both. It can mean eking out a living in the shadows, and it can also mean thriving in the warmth of forests that stretch to the poles. Both shaped the dawn of the Age of Mammals. They are gone now, entirely vanished, yet for a span of over 100 million years they were among the most enduring mammals to ever live. The Multituberculates, often shortened in the paleontological literature to multals, flourished from the Jurassic into the Eocene, and for much of that span they were the quiet background players of Earth's ecosystems. Their record stretches so long that when dinosaurs ruled, Multituberculates scurried at their feet, and when dinosaurs died, Multituberculates remained. They outlasted lineages we think of as far more resilient, only to fade just as the Age of Mammals was supposed to be their chance. The haunting question is, why did the longest-lasting mammal lineage fail in a world seemingly built for them? Fossil evidence gives us our clearest insight into these enigmatic creatures. Their name itself comes from the rows of cusps on their molars, many little tubercles lined up in patterns unlike any other mammals. This distinctive dentition made them instantly recognizable in the fossil record and hints at their extraordinary versatility. In small-bodied Jurassic forms such as Cryptobartar, the teeth suggest insectivory and omnivory. In later Paleocene and Eocene representatives like Tinilabis, their molars had evolved into formidable grinding tools, capable of shredding plant matter, seeds, and perhaps even the earliest grasses. These teeth were their signature adaptation, a self-sharpening system that remained remarkably consistent across tens of millions of years. What is striking is how squirrel-like many of them appear in reconstructions. Some, like Tilodus, show elongated fingers and flexible ankles, features interpreted as adaptations for climbing. Fossils reveal curved claws that could grip bark and branch, and their long tails likely provided balance as they leapt among canopy shadows. Others became ground dwellers, with sturdy bodies and gnawing incisors that look astonishingly rodent-like. Yet despite the resemblance, they were not rodents. They represent a separate branch of mammalian evolution, one that split from our own very early and pursued its own experiment in tooth design and lifestyle. For over 100 million years, that experiment seemed successful. During the earlier Cenozoic, in the aftermath of the impact, Multituberculates were among the creatures that endured. Their generalized diets, their small size, and their ability to climb and hide in complex habitats made them suited for a recovering world. Fossils from North America show them rapidly diversifying in the Paleocene, with some genera reaching sizes comparable to modern beavers. 𝐓𝐈𝐌𝐿𝐄𝐒𝐓𝐀𝐌𝐿𝐄𝐒𝐓𝐀𝐌𝐄𝐒 known from the Nacimiento Formation in New Mexico, may have weighed over 100 kilograms, making it the largest multituberculate ever known. These were not marginal creatures eking out survival in the shadows anymore. They were browsing on tough vegetation, gnawing at seeds, and occupying herbivorous niches left vacant by the dinosaurs. For a time, the Age of Mammals was also the age of multituberculates. They spread across continents, from Asia to North America and Europe. Their fossils appear in forest deposits alongside early primates, marsupials, and archaic hoofed mammals. In some places, they represented the majority of mammalian species present. Their tooth structure allowed them to process food efficiently, giving them an advantage in forests full of angiosperms and seeds. Their climbing forms may have been among the first mammals to take full advantage of complex canopies, competing with birds and early primates for fruit and insects. But their rise is also puzzling because by 40 million years ago they're gone. The decline was not sudden, like the abrupt extinction of non-avian dinosaurs, but a long dwindling. In North America, they vanished from the fossil record during the early Eocene. In Asia, their lineage lingers a little longer but eventually disappears as well. We are left with a mystery. Why did the longest-lived mammalian order die out in a time when mammals overall were thriving? Several hypotheses circulate among paleontologists. One centres on competition. Their teeth, though versatile, may have been less efficient than the specialised gnawing system of true rodents, who appear in the Paleocene and diversify rapidly in the Eocene. Rodents developed ever-growing in sizes with enamel restricted to the front face, creating natural chisels that stayed sharp with wear. Multituberculates had powerful gnawing teeth too, but their design did not allow for the same self-maintenance. In a world of expanding seed and nut resources, rodents may simply have been better equipped. Another line of reasoning points to ecological changes. As the Paleocene gave way to the Eocene, climates shifted, forests thinned in some regions, and open habitats became more common. Multituberculates, particularly those specialised for arboreal life, may have lost ground as their favoured environments receded. Rodents, primates, and other placental mammals diversified into new niches that multis did not seem to enter. What we know from the fossil record suggests that multituberculates did not radiate into aquatic or cursorial forms. They did not become bat-like flyers or antelope-like runners. Their adaptations remained constrained, successful for a time but limited in scope. There is also the possibility that their very success in the Paleocene locked them into particular roles. Taeniolabis and its kin grew large, but they remained herbivores with grinding teeth, not predators or mixed feeders. Their ecological range may have been too narrow to withstand competition once more dynamic groups emerged. When the Eocene saw the rise of primates in the canopy, rodents on the ground, and carnivorans beginning to assert themselves, the multituberculates found themselves squeezed. What is humbling is how incomplete the evidence still is. We have jaws, teeth, and some postcranial bones. From these we infer diet, lifestyle, and decline. But the direct causes remain speculative. Did rodents truly outcompete them head-to-head, or was it simply that environmental shifts favoured rodent versatility? Did diseases, parasites, or other unknown factors play a role? We cannot be certain. The fossil record, as always, whispers more than it shouts. Yet their story is essential to understanding mammalian history. For over 100 million years, multituberculates demonstrate that mammals were not simply passive shadows under the reign of reptiles. They were adaptive, diverse, and successful in their own right long before placentals came to dominate. Their extinction in the early Cenozoic reminds us that longevity is no guarantee of permanence. Even the most resilient lineages can falter when environments shift or new competitors emerge. When we look at a squirrel today, or a beaver gnawing at wood, it is tempting to imagine we are seeing echoes of the multituberculates. Their rodent-like features were convergent, but they capture a parallel possibility of what mammalian success could have looked like. Had they endured, perhaps we would speak today of a world shaped by multis rather than by rodents and primates. Instead, their bones rest in museum drawers, their teeth lined with the little tubercles that gave them their name, a testament to an experiment in mammalian evolution that lasted longer than almost any other and still came to an end. The haunting question lingers. What does it mean for a lineage to succeed? Is it the length of time it persists, or the legacy it leaves behind? Multituberculates lived for over 100 million years, survived the extinction that killed the dinosaurs, and spread across continents. Yet they left no descendants. Their story ends abruptly, with no living representatives to carry forward their genetic memory. They remind us that evolutionary success is not a straight line toward us, but a branching thicket where even the strongest branches can wither. For tens of millions of years after the dinosaurs fell, South America was an island continent adrift in warm seas, separated from North America, Africa, and Antarctica. This isolation created a peculiar laboratory of evolution, where marsupials became rulers, diversifying into roles filled elsewhere by placental mammals. The fossil record reveals an empire of marsupials unlike anything alive today, a world where predators and prey followed parallel but separate trajectories, shaped by convergence yet distinct in origin. The question that drives this story is how marsupials, often imagined today as restricted to Australia, and a few opossums in the Americas, once dominated an entire continent as apex carnivores and abundant herbivores. The key players of this South American stage were the Spracodonts, an order of carnivorous marsupials that range from small weasel-like forms to large, bone-crushing hunters. Fossil deposits such as those at Patagonia and La Venta in Colombia preserve their bones in startling detail. Early genera like Myalestes suggest a small-bodied predator that lived in the Paleocene around 60 million years ago. With flexible ankles and sharp shearing teeth, it would have resembled a small civet or mongoose, scurrying through forests and preying on insects and small vertebrates. From such modest beginnings, the Sparassodonts would radiate into a bewildering variety of forms. By the Oligocene, around 35 million years ago, Sparassodonts included lineages that bore uncanny resemblance to placental carnivores. The Boryenids were robust, with heavy skulls and strong jaws, converging on dog-like or bear-like body plans. Fossilized jaws show powerful carnassial teeth capable of slicing flesh, much like those of placental carnivores in the northern continents. This is convergence written in bone, two unrelated lineages evolving nearly identical tools for the same ecological role. The resemblance was not superficial. Skeletal reconstructions suggest they walked with plantigrade or semi-digitigrade stances, hunted medium to large prey, and lived much as wolves or hyenas would have lived elsewhere. The most remarkable Sparassodont, and perhaps the most iconic, was 𝐓𝐈𝐌𝐿𝐼. Emerging in the Miocene and persisting until only a few million years ago, 𝐓𝐈𝐿𝐼 was a marsupial saber-tooth. Its skull bore enormous downward-curving canines that extended beyond the lower jaw, even when the mouth was closed. Unlike the saber-toothed cats of the north, these teeth were continuously growing, protected by bony flanges of the lower jaw. Muscle attachments suggest it may not have had as powerful a bite as placental saber-tooths, but its shearing action would have been devastating to soft tissue. In life, it may have stalked the pampas and forests of South America, ambushing prey in a manner eerily reminiscent of Smilodon, a predator it would never have met, but one whose existence elsewhere shows how evolution finds the same answers to the same problems. This marsupial carnivore guild was not limited to saber-tooths and dog-like hunters. There were nimrovids of the marsupial world, slender, climbing forms that chased prey into trees. There were robust scavengers that could crack bones. There was even evidence of herbivorous marsupials filling roles similar to ungulates, though these never reached the same ecological dominance as their carnivorous kin. In the isolation of South America, marsupials filled almost every ecological role, from small insect hunters to apex predators weighing over 100 kilograms. Why did marsupials succeed so spectacularly in South America? Part of the answer lies in geography. With the continent cut off from other land masses, placental carnivores could not migrate in, leaving niches open. The opossum-like ancestors of Sparassodonts expanded into those niches with evolutionary freedom. They already possessed the basic carnivorous toolkit: sharp teeth, flexible limbs, and varied diets. Isolation meant they did not have to compete directly with placental carnivores until much later. Another factor was the environment itself. South America during the Paleocene and Eocene was covered in lush forests and wetlands, teeming with prey animals, including the early ungulate-like ungulates and litopterns that themselves were unique to the continent. Marsupial predators had no shortage of opportunities. The fossil evidence shows that these ecosystems were not primitive or impoverished. They were as complex and competitive as any ecosystem today, simply structured with different players. In Patagonia's Santa Cruz Formation, dated to the Miocene around 18 million years ago, bones of Sparassodonts lie alongside those of ground sloths, glyptodonts, and early monkeys. The presence of large marsupial predators in such communities demonstrates they were apex hunters, not fringe participants. They were the lions and tigers of their world. But even in their heyday, the seeds of decline were present. Sparassodont diversity peaked in the Oligocene and Miocene, but their numbers dwindled in the late Miocene and Pliocene. By the time the Isthmus of Panama rose around 3 million years ago, connecting North and South America, marsupial empires were already faltering. The arrival of placental carnivores from the north, cats, bears, canids, accelerated their extinction, but they had been in retreat before that event. Why? Some paleontologists suggest that changes in climate and habitat played a role. South America gradually shifted from dense forests to more open grasslands during the Miocene. Sparassodonts, many of which were ambush predators in wooded settings, may have struggled in open plains. placentals that later entered the continent were already adapted to such environments, giving them an advantage. Other hypotheses point to the possible reproductive limitations of marsupials compared with placentals. Marsupials generally have longer maternal care periods and lower reproductive rates, which may have made them less resilient to ecological stress. Still, the fossil record forces us to be humble. We see the bones, the jaws, the wear patterns on teeth, but not the full picture of behaviour, social structure, or adaptability. We cannot know whether Thylacolmylus hunted in groups or alone, whether Boreanids scavenged as often as they killed, or how flexible their diets truly were. What we do see is that for tens of millions of years, marsupials were not restricted to the ecological margins. They were front and centre, shaping ecosystems and preying on some of the most remarkable herbivores ever to evolve in isolation. Their eventual disappearance invites reflection. Were marsupials destined to lose to placentals, or was it a matter of timing and geography? If South America had remained isolated longer, might Sparassodonts still stalk the forest today? The answer is unknowable, but the thought is sobering. We often view marsupials through the lens of Australia, where they endured without placental competition. South America offers a mirror story. When marsupials stood alone, they could rule entire continents. Their decline was not inevitable, but contingent on shifting climates and the eventual collapse of isolation. What lingers is the reminder that dominance in evolution is always temporary. South America's marsupial predators held sway for over 30 million years, longer than humanity has yet existed, yet they are gone. The fossil record preserves their jaws and sabres, their convergent echoes of placental hunters, but no living heirs roam the pampas. Their story is a vanished empire, a lesson in both the power of isolation and the fragility of ecological reigns. When we say the phrase Age of Mammals, it is easy to forget how uncertain the very definition of a mammal once was. To us, it feels obvious. Mammals have fur, they nurse their young, they hear with a delicate chain of 3 bones, and they chew with a jaw hinged from a single joint. Yet when we trace those traits back into deep time, the neat categories dissolve into a gradient of forms. Some of the features appear early, in creatures that are not quite mammals. Others arrive piecemeal, millions of years before the first crown mammals emerge. The question that naturally follows is deceptively simple. What exactly makes a mammal a mammal? In modern biology, the answer begins with the crown group. Crown group mammals are defined as the living monotremes, marsupials and placentals, plus all their descendants back to their most recent common ancestor. This is a taxonomic anchor point, a way to draw a boundary through a confusing fossil record. But of course, evolution did not move with tidy lines. It shuffled traits, borrowed structures, and rewired bones. Creatures that lived alongside early dinosaurs may look mammalian at first glance, but lie just outside that crown. Paleontologists group them as mammalia forms, a broader circle that includes close relatives of true mammals, but not quite within the living definition. The story of mammalian traits stretches back at least to the late Triassic, around 215 million years ago, when creatures like Morganocodon scurried through fern forests in what is now Europe and China. To an untrained eye, Morganocodon might look like any shrew, but its jaw reveals the subtle duality of its place in history. Earlier relatives had a jaw composed of several bones, with the articular and quadrate forming the hinge. In Morganocodon, a second hinge emerged, linking the dentary to the squamosal bone of the skull, the same joint we use to chew today. The old joint still remained, the bones reduced in size but still functional. Over evolutionary time, those bones migrated fully into the middle ear, becoming the malleus and incus. In this way, the mammalian ear was born through the reallocation of parts once belonging to the jaw. This transformation is one of the most celebrated examples of evolutionary tinkering. It demonstrates that complex new structures can arise not from sudden invention, but from gradual repurposing. For Morganocodon, this dual joint system suggests a transitional stage where hearing became more sensitive while chewing efficiency also improved. Its existence is a fossil snapshot of a process that we otherwise could only infer. It also reminds us of how piecemeal evolution can be. At the time of Morganocodon, fur was probably already present, lactation may have been developing, but the definitive three-bone ear of crown mammals had not yet fully detached. It was a creature both ancient and modern in a single body. Further along the timeline, another tiny mammalia form, 𝐓𝐻𝐿𝐿, appears in the early Jurassic. Though smaller than a mouse, its skull suggests that the middle ear bones had already detached from the jaw. This means the hallmark of mammalian hearing may have originated earlier than once believed. If so, then the ability to detect higher frequencies and subtle sounds may have given these small nocturnal insect hunters a crucial advantage in worlds dominated by reptiles. Hearing prey in the leaf litter or predators moving nearby could mean the difference between survival and oblivion. Another clue comes from a fossil described only recently, the Middle Jurassic Microdocodon. What made this discovery remarkable was not its teeth or jaw, but a tiny structure in the throat, the hyoid bone. In mammals, the hyoid forms a saddle-shaped structure that anchors the tongue and supports the mechanics of suckling. Reptiles lack this complexity. Their hyoid is a simple rod. The hyoid of Microdocodon is delicate with movable joints much like ours, suggesting that even this distant relative had already evolved the ability to suckle milk. Though we cannot see the mammary glands themselves, the skeletal hint tells us lactation was almost certainly part of its biology. If true, then the intimate bond of mammal mothers feeding their young with milk stretches back nearly 200 million years. Fur, though even more elusive in the fossil record, also pushes back into deep time. Fossilized droppings from the Permian period, before the dinosaurs themselves, contain what appear to be hair fragments. These coprolites are attributed to therapsids, the reptile-like ancestors of mammals. This suggests that hair, perhaps first serving as sensory whiskers or insulation, long predates the crown group. Later, specimens like the Jurassic castor recorder preserve impressions of fur, providing direct evidence that mammalia forms were already cloaked in hair while dinosaurs still reigned. Each of these traits, fur, lactation, the three-bone middle ear, and the dentary squamosal jaw joint, emerged at different times in different lineages. The crown group definition gathers them into one package, but in reality, evolution stitched them together gradually. This is why the boundary between mammal and not quite mammal is blurry. It is not a single step, but a long corridor with many doorways. Fossils like Morganucodon, 𝐓𝐻𝐿𝐿, and Microdocodon allow us to peek through those doorways, but we still cannot reconstruct the entire corridor. By the dawn of the Cenozoic, when dinosaurs were gone and mammals began to flourish in earnest, these traits had coalesced. Crown mammals were small, but they carried within them the complete suite of features we recognise today. They had fur to regulate their body temperature in fluctuating climates. They could hear with delicate ears tuned to subtle sounds. They could nourish their offspring with milk, extending parental care beyond the moment of birth. They chewed with efficient jaws that allowed diverse diets. These advantages did not guarantee success. Many mammal lineages still vanished, but they laid the foundation for flexibility in a world now open to new possibilities. It is tempting to see inevitability in this story, to imagine mammals waiting patiently in the wings until their time came. But the fossil record warns us against such neat narratives. For tens of millions of years, mammalia forms existed alongside dinosaurs without ever achieving dominance. Many of their lineages died out without descendants. The features we now call mammalian were not a destiny, but a collection of lucky innovations tested again and again in a changing world. That we can trace them backward at all is only because fragments of jaws, ears, and hyoids happen to fossilize and be found. Much is still hidden. The haunting resolution is that we may never pinpoint the exact moment the first mammal appeared. Definitions shift as new fossils are discovered. What we can say is that by the early Cenozoic, the animals that survived carried the unmistakable signature of mammalian life. They were no longer transitional, but firmly within the crown. From that point forward, the story is not about what makes a mammal, but about what mammals would do with those traits in a world remade. In the world left behind by the dinosaurs, one of the most urgent ecological roles waiting to be filled was that of the predator. Apex carnivores had been reptilian for well over 150 million years, from the toothy archosaurs of the Triassic to the tyrannosaurs and dromaeosaurs of the Cretaceous. When those animals were extinguished by the impact and its aftermath, the mammalian survivors were left in a landscape of small bodies and unclaimed niches. The question was which lineage would seize the opportunity to become the dominant hunters of the Cenozoic. The answer, at least for the first 20 million years, was not the ancestors of modern cats or dogs, but a now vanished order called the creodonts. Their story is a reminder that the predators we take for granted today were not always the ones at the top. Creodonts first appear in the Paleocene, around 60 million years ago. They belong to a group of placental mammals distinct from the crowned carnivores we recognise today. Their name comes from the Greek for meat teeth, and the name is fitting, because their defining feature was the evolution of specialised carnassial teeth. These were self-sharpening blades formed from the last upper premolar and the first lower molar, designed to slice meat efficiently. This arrangement was not inherited from earlier ancestors, but developed independently, parallel to the carnassial system of true carnivores. In other words, two different mammalian lineages converged on the same solution to the problem of tearing flesh. Early creodonts, such as Archaea, were small and generalised, not yet apex hunters, but already showing the dental adaptations that marked their lineage. As the Paleocene progressed into the Eocene, creodonts diversified. Families such as the hyaenodonts and oxyaenids spread across North America, Europe, Africa and Asia. Their body forms range from slender, tree-climbing predators to massive bone-crushing hunters weighing several hundred kilograms. Some resembled wolves, others hyenas, others even big cats in their ecological role, though the resemblance was only skin-deep. Fossil skulls reveal long, narrow snouts, large slicing teeth, and relatively small brain cases. Among the most formidable was Pterodon, a hyaenodont known from the Eocene of Europe and Africa. With a skull nearly half a metre long, it would have been a powerful predator capable of tackling large herbivores. In North America, Oxyaena and Patriofelis filled similar roles. Reconstructions of Patriofelis suggest a squat, heavily built animal, perhaps semi-aquatic, preying on fish and mammals along rivers. Other genera, like Sarcastodon from Mongolia, reach truly terrifying sizes, estimated at over 400 kilograms. Its teeth and jaw mechanics suggest it could shear flesh with devastating efficiency, placing it at the top of Eocene food chains. For tens of millions of years, creodonts were the dominant mammalian predators across much of the Old World. Their fossils are often found alongside those of early ungulates, suggesting a predator-prey dynamic similar to that of modern carnivores and herbivores. They even occupied ecological roles later filled by big cats and hyenas. Some crushed bone, others specialised in ambush, others in pursuit. The Eocene was, in many regions, an age of creodont dominance. At the same time, another lineage of carnivorous mammals was stirring. These were the maiacids, small and weasel-like animals that represent the stem group of modern carnivorans. They first appear in the Paleocene as well, around 55 million years ago, but for millions of years they remained small, generalised hunters, preying on insects, small vertebrates, and perhaps scavenging. Their teeth lacked the highly developed carnassials of creodonts, and their bodies were not built for tackling large prey. In the shadow of creodonts they were minor players. Yet from these maiacids would come every carnivoran alive today: cats, dogs, bears, hyenas, seals. The parallel existence of creodonts and maiacids created a long overlap. For nearly 20 million years, two different groups of carnivorous mammals hunted side by side, one destined for extinction, the other for ascendancy. The reasons for this eventual reversal are still debated. One possibility is rooted in anatomy. In creodonts, the carnassials were placed farther back in the jaw, limiting the grinding surface available for other functions. In true carnivorans, the carnassials sit more forward, allowing additional molars behind them for crushing or grinding. This difference may have given carnivorans more dietary flexibility, letting them adapt to changing prey bases as climates shifted. Another possibility lies in locomotion. Fossil limb bones suggest creodonts often had sprawling or semi-sprawling postures, less efficient for long-distance running. Carnivorans, by contrast, evolved more erect postures and flexible spines, adaptations that would eventually produce swift pursuit hunters like dogs and cheetahs. In a world where herbivores were becoming faster and more specialised, this difference in speed and endurance may have mattered greatly. Climate change also played a role. The late Eocene into the Oligocene saw significant global cooling and the spread of more open habitats. Forest-dwelling ambush predators like many creodonts may have been disadvantaged, while carnivorans were pre-adapted for open country pursuit. The fossil record shows creodont diversity declining in the late Eocene, while carnivorans expanded. By the Miocene, creodonts were gone, their roles entirely usurped by carnivorans. What is most striking is how completely they disappeared. No creodonts survive today. They left no direct descendants, only bones in rock layers and convergent echoes in later predators. The entire lineage, once the terror of Eocene plains and forests, is erased. Their extinction is a reminder that dominance in evolution is fragile. Even lineages that thrive for tens of millions of years can vanish, leaving room for others to rise. The haunting question is why creodonts, with all their success, could not persist. Was it a slow erosion of ecological ground, a steady outcompeting by carnivorans more flexible in diet and locomotion? Or were there abrupt crises, perhaps shifts in prey populations, that left them stranded with over-specialized jaws? We may never know with certainty. What we do know is that their story complicates the narrative of inevitability. Carnivorans were not destined to rule. For much of the early Cenozoic they were marginal, while another lineage held the crown. Only by chance, climate and anatomy did the balance shift. When we look back at the jaws of Sarcastodon or the skeleton of Oxyaena, we see not failures but alternative histories. The Age of Mammals could have been theirs, with carnivorous lineages wholly unrelated to ours still dominating today. Instead, their bones lie in museum drawers. Their evolutionary experiment ended. Their story is both fascinating and humbling. Predators before predators, carnivores before carnivores, a reminder that the world we see now is only one of many paths evolution once explored. In the aftermath of the asteroid and the collapse of the great reptilian herbivores, the land was covered in greenery waiting to be eaten. Forests of angiosperms spread widely, swampy lowlands were filled with aquatic vegetation, and shrubs and understories flourished in the warm Paleocene world. Yet for millions of years no true ungulates existed as we know them now. The plant-eating niches were occupied by strange experiments, mammals that do not belong to any living lineage, animals that appear in the fossil record as if they were trial runs in the evolutionary workshop. They were the condylarths, arctocyanids, phenacodonts, pantodonts, and their kin, each with peculiar adaptations that briefly flourished and then vanished. The question their bones pose is why so many of these early herbivore experiments failed, even after tens of millions of years of success. The condylarths are perhaps the most enigmatic. Their very name has become something of a paleontological wastebasket, used historically to describe many early hoofed-like mammals that defied neat classification. They appear shortly after the extinction, by 60 million years ago, and range from mouse-sized omnivores to dog-sized browsers. The uniting feature was their generalized teeth, with low cusps suggesting a diet of leaves, fruits, and perhaps small amounts of meat. In life they may have looked superficially like raccoons or coatis, scampering on the forest floor or climbing through branches, yet their limb bones show hints of hooved toes, suggesting the first steps toward the ungulate body plan. Still, their anatomy was not specialized enough to persist. Condylarths are often called archaic ungulates, but most lineages left no descendants, fading by the Eocene without ever producing the giants of later times. Among them, one of the most intriguing groups was the arctocyanids. These were larger-bodied animals, some the size of bears, with powerful limbs and long tails. The very name arctocyan means bear dog, a reflection of their odd, ambiguous anatomy. Fossils suggest a mixture of herbivorous and carnivorous traits. Their teeth were capable of shearing flesh, but also grinding plant matter, marking them as omnivores or opportunists. Some paleontologists believe they may have been arboreal predators, while others see them as ground-dwelling omnivores. Their ecological role remains debated, but what is clear is that they were diverse and widespread in the Paleocene. By the early Eocene, however, they declined sharply. Their generalized habits, once advantageous in unstable ecosystems, became liabilities when more specialized herbivores and carnivores emerged. A more focused step toward herbivory came with the phenacodonts. These were early herbivores that lived between 60 and 55 million years ago, and their teeth show adaptations for grinding fibrous plant matter. Venacodus, the most famous of the group, was a sheep-sized animal with elongated limbs and simple hooves on its toes. Its skeleton suggests it could run more efficiently than the lumbering arctocyanids, perhaps giving it some defense against predators. In Phenacodus, paleontologists see one of the earliest true herbivorous body plans: long legs, hooved digits, and teeth shaped for browsing. Though not directly ancestral to later ungulates, they reveal the gradual steps toward the familiar forms of horses and cattle. Yet the phenacodonts themselves eventually disappeared, leaving only their anatomical echoes in later lineages. The pantodonts represent another branch of early experiments, and their fossils reveal some of the strangest mammals of the Paleocene and Eocene. These were large-bodied herbivores, among the first mammals to reach true gigantism after the extinction. Coryphodon, for instance, reached the size of a modern tapir, with a barrel-shaped body and short limbs. It lived in swampy environments, browsing on aquatic plants. Fossilized teeth show heavy wear, evidence of a diet of tough vegetation. Coryphodon had a broad snout and small brain case, suggesting a slow-moving grazer that relied on bulk rather than speed. Even more peculiar was Lambda, a pantodont that lived in North America around 55 million years ago. It weighed as much as 600 kilograms, with a long heavy tail that may have acted as a prop when it reared on its hind legs to browse high vegetation. Its massive skull and chisel-like front teeth are unlike anything in living herbivores. Reconstructions suggest a hulking, sloth-like animal lumbering through Paleocene forests, immune to predation by virtue of size alone. For millions of years, pantodonts were the giants of their ecosystems, filling the role of mega-herbivores left vacant since the extinction of the last sauropods. Yet despite their early success, pantodonts also vanished. By the Middle Eocene, they were gone, replaced by more advanced ungulates. Their teeth and digestive systems may not have been efficient enough for the tougher plants that spread as climates cooled and forests opened. Their lumbering forms, once adequate, became maladaptive in a world where predators grew swifter and competitors more efficient. The pantodonts, like the arctocyanids and condylarths, became evolutionary dead ends. What unites all these early herbivore experiments is their impermanence. They thrived in the Paleocene, when ecosystems were still recovering and ecological roles were open to improvisation. But as climates shifted and more modern lineages evolved, these pioneers could not keep up. Their fossils, scattered across North America, Europe and Asia, record an age when mammalian herbivory was still in flux, when no single lineage had yet achieved dominance. For paleontologists, they are both frustrating and fascinating. Frustrating because their relationships to later mammals are often unclear. Fascinating because they show the breadth of experimentation that occurred in the wake of disaster. It is humbling to recognise that many of these animals lived for millions of years, longer than our species has yet existed, and still left no legacy. They remind us that survival is not the same as success in evolutionary terms. A lineage can endure vast stretches of time, dominate landscapes, and still vanish without a trace in the modern world. In this sense, the condylarths and pantodonts are like ghost branches of the mammalian tree, flourishing brilliantly and then cut short. The haunting question is whether their disappearance was inevitable. Were they doomed by intrinsic limitations, their teeth and limbs too crude to compete with the refinements of later ungulates? Or were they victims of contingency, accidents of climate and geography that could have gone differently? If Earth's history had tilted another way, might our plains today be filled with pantodonts instead of antelopes, with phenacodonts instead of horses? The answers lie buried, partial, and incomplete. What we can say is that the Age of Mammals began not with familiar creatures, but with strange and fleeting experiments, each testing what it meant to be a large plant-eater in a world newly open to mammals. When the asteroid struck at the end of the Cretaceous, it erased animals of a size that had not existed before or since. For a brief time, Earth was left with small survivors, a world of mammals no larger than foxes and birds no larger than turkeys. Yet within only 10 to 15 million years, the first true giants of the mammalian age appeared. By the early to middle Eocene, creatures rivaling rhinoceroses and even small elephants roamed the forests and floodplains. The question that has fascinated paleontologists for more than a century is how quickly mammals returned to such monumental size, and why gigantism re-emerged at all in a world that had seemed reset to smallness. One of the most striking of these early giants was Wintertherium, a beast that lived around 55 to 40 million years ago in what is now North America. Its fossils, first discovered in Utah in the 19th century, gave the animal its name, which means beast of the winter mountains. In life, Wintertherium stood nearly 2 meters tall at the shoulder and weighed as much as 2 tons. Its skull was massive, ornamented with bony knobs that may have supported skin or horn coverings, and its jaws carried long, saber-like canine teeth. Despite its fearsome dentition, it was a herbivore, using its front teeth and grinding molars to consume tough vegetation. Reconstructions often show it with a vaguely rhinoceros-like body, though its lineage was entirely separate, belonging to a now extinct group called the Dinoceratans. Wintertherium was not alone. Its relatives in the Dinoceratan order spread across North America and Asia, forming a brief but spectacular radiation of giant herbivores. Their skulls often bore elaborate bony growths, hinting at displays or combat between males, and their skeletons suggest powerful, slow-moving bodies. These animals were among the first mammals to reclaim the ecological role of megaherbivore after the extinction, a role once monopolized by sauropods and ceratopsians. For perhaps 10 million years, Dinoceratans dominated the floodplains, only to disappear entirely by the late Eocene, leaving no descendants. Meanwhile, in Asia, another strange giant appeared. Ungulates, known only from a single skull discovered in Mongolia and described in the 1920s, has become one of the most enigmatic mammals of the Eocene. The skull alone measures nearly a meter in length, with a long snout and massive jaws. Its teeth suggest an omnivorous or carnivorous diet, capable of shearing flesh but also grinding bone or plant matter. Estimates of its body size vary widely, but some reconstructions propose an animal weighing several hundred kilograms to over a ton, making it perhaps the largest terrestrial carnivorous mammal of its time. Its exact affinities remain debated, with some studies linking it to the artiodactyl lineage that would later include hippos and whales. Whether predator, scavenger, or omnivore, Ungulates represents the rapid expansion of mammals into giant body sizes even on the carnivorous side of the spectrum. The return of gigantism in the Eocene was not limited to these headline species. Titanotheres, relatives of horses and rhinoceroses, also began to grow large during this period, filling open habitats with bulky herbivores. The ground sloth precursors of South America began their slow rise toward impressive sizes as well. Across the continents, mammals were testing the upper limits of body mass, evolving into forms that pushed against the same boundaries of physics and ecology that once constrained dinosaurs. Why did gigantism reappear so quickly? The answer likely lies in both opportunity and environment. The Paleocene world had been dominated by small generalists, but as forests matured and ecosystems stabilized, resources became abundant. Plants grew tall, fruits and seeds proliferated, and open floodplains provided expanses of forage. In such contexts, large body size offered clear advantages. A giant herbivore could reach higher vegetation, process larger volumes of low-quality food, and deter predators simply by size. Large carnivores in turn evolved to exploit the growing herds of herbivores. Evolutionary arms races, long a feature of the Mesozoic, began again in mammalian form. There were also climatic factors. The early Eocene, around 55 million years ago, was one of the warmest intervals of the Cenozoic. Tropical and subtropical climates extended to high latitudes, and lush vegetation spread across much of the globe. In such productive environments, ecosystems could support larger animals. Fossil forests in the Arctic reveal broadleaf trees and crocodilian remains, reminders of the abundance of life in climates that today seem inhospitable. The combination of warmth and productivity may have allowed mammals to experiment with size much sooner than would have been possible under harsher conditions. Yet gigantism came with risks. The enormous Dinoceratans disappeared by the end of the Eocene, and Ungulates has no close descendants. Titanotheres too would rise to prominence only to vanish in the Oligocene. Large size offers resilience against predation, but makes species vulnerable to environmental change. When climates cooled and habitats shifted, giants often found themselves stranded. The repetition of this pattern across different lineages suggests that gigantism is less a permanent strategy than a recurring experiment, one that evolution conducts again and again in times of abundance. What remains of these animals today are bones, often fragmentary, that force us to imagine bodies far larger than the creatures that survived the impact. To hold a Ungulates skull, or gaze at the immense jaw of Andrewsarchus, is to confront the speed at which life rebounded after catastrophe. In a geological instant, mammals leapt from mouse-sized survivors to rhino-sized behemoths. The rapidity of this transformation is astonishing, and it challenges the notion that evolution always moves slowly. Under the right conditions, abundant resources, open niches, favourable climates, size can increase dramatically within only a few million years. The haunting question is what these early giants tell us about the nature of success. Were Wintertherium and Andrewsarchus evolutionary triumphs, proof that mammals could reclaim the world once held by dinosaurs? Or were they cautionary tales, short-lived experiments that show the limits of gigantism? Their extinction suggests the latter, yet their very existence reshaped ecosystems and paved the way for later lineages. Giants, it seems, are both inevitable and temporary, rising quickly when opportunity allows, but always vulnerable to the next turn of climate and competition. The story of gigantism in the Eocene also highlights how mammals began to interact with one another at larger scales. When small insectivores and omnivores dominated the Paleocene, predator-prey relationships were limited to encounters of fox-sized hunters and rodent-sized prey. With the rise of multi-ton herbivores like Wintertherium and massive predators such as Andrewsarchus, ecosystems gained new dynamics. Fossil trackways and bone beds suggest that these giants did not live in isolation, but likely moved in groups, creating pressures on landscapes and shaping vegetation patterns. Browsing by a herd of Dinosaurians could have stripped large areas of foliage, in turn influencing the distribution of smaller herbivores and the carnivores that hunted them. In this way, the reappearance of giant mammals fundamentally altered the fabric of terrestrial life, much as sauropods and ceratopsians had done before them. One of the more intriguing aspects of these early giants is how they combined primitive and advanced features. The skulls of Dinosaurians look bizarre compared with modern herbivores, bearing horn-like protrusions whose exact purpose remains debated. Were they for sexual display, species recognition, or combat between rivals? We cannot be certain. Their teeth, though suited for grinding vegetation, lack the complex patterns seen in later ungulates, suggesting they may not have been highly efficient feeders. In contrast, their large body size hints at abundant food and the ability to process bulk plant matter, even without refined dentition. This mosaic of features reminds us that evolution often produces functional but temporary solutions, cobbling together traits that work for a time but will later be replaced by more specialized systems. The rise of giant carnivores like Andrewsarchus also carries lessons about ecological opportunity. Without competition from other large predators in Asia during the Middle Eocene, a lineage related to artiodactyls could grow into the role of apex hunter. It is a reminder that evolutionary success is not always about superior design, but about timing and vacancy. When niches are open, even lineages not typically associated with predation can evolve into formidable carnivores. That Andrewsarchus did not persist may say less about its abilities and more about the fragility of such opportunities. When climates shifted and competitors evolved, its ecological experiment ended. Another important element is dispersal. The Eocene was a time of relatively warm climates and high sea levels, but continental connections still existed. Land bridges across the northern Atlantic and through Beringia allowed exchanges between North America, Europe and Asia. Giants like Dinosaurians are found on both continents, indicating that once large body sizes evolved, they could spread rapidly across vast distances. This dispersal capability helped reinforce gigantism as a repeating pattern. Once a lineage achieved large size in one region, it could colonize others, ensuring that ecosystems across the northern hemisphere contained their own versions of giants. Ultimately, the giants of the Eocene remind us that Earth's ecosystems are rarely static. Just as dinosaurs once grew to immense size in response to opportunities and constraints, mammals did the same when the world permitted it. Their rise was rapid, their dominance impressive, but their decline inevitable as environments changed. The lesson is not that gigantism guarantees long-term success, but that it is one of evolution's recurrent strategies. appearing when energy is plentiful and vanishing when the balance shifts. That the first mammalian giants emerged so soon after the impact underscores how quickly life can rebound from catastrophe, reshaping itself into new forms that echo the giants of the past while foreshadowing the giants yet to come. What were the first primates like, and why did they matter? When we picture primates today, we imagine lemurs leaping across Madagascar's forests, monkeys foraging in social troops, or apes scrutinizing us with familiar unnerving eyes. But long before these recognizable forms emerged, there was a quieter beginning, tucked into the branches of Paleocene and Eocene forests. The world between 55 and 40 million years ago was warm, humid, and draped in continuous canopies of green. These lush landscapes provided a crucible for experimentation, where small mammals could climb, leap, and adapt to new ways of sensing their environment. It was in this greenhouse world that the first true primates appeared, and while they might not have looked like us, they carried within them the traits that would one day shape our own story. The earliest candidates for our lineage are often grouped under the name Plesiadapi forms, a collection of archaic mammals that thrived in the Paleocene and lingered into the early Eocene. To the casual eye, they looked like rodents or tree shrews, with elongated bodies, long tails, and gnawing incisors. Some, like Plesiadapis, grew to the size of a house cat, while others were small enough to fit in a human palm. They lacked many of the hallmark features of later primates, such as forward-facing eyes or grasping hands, which has led to debate about whether they should be considered true primates or merely close relatives. Their skeletons, however, show important shifts. Some had flexible ankle joints suited for climbing, and their dentition suggests diets ranging from fruits and leaves to insects. They may not have been primates in the strictest sense, but they occupied the ecological spaces that would soon be taken over by them, bridging the evolutionary gap between generalized mammals and more specialized arboreal primates. By the early Eocene, around 56 million years ago, we find the first clear evidence of true primates. These are grouped into two broad lineages: the Adapiforms, which resembled modern lemurs, and the Amomniforms, which were smaller, more nocturnal creatures with traits reminiscent of tarsiers. The Adapiforms included animals like Adapis, whose fossils were first described in the late 18th century and sparked some of the earliest debates about primate evolution. They were medium-sized, diurnal, and adapted for life in the trees, with grasping hands and feet, nails instead of claws, and forward-facing eyes that improved depth perception. The Amomniforms, such as Talardina, were smaller and likely insectivorous, with larger eyes suited for night vision. This split between day-active, fruit-eating forms and nocturnal insect-hunting ones foreshadows the ecological diversity that would later define primates. The adaptations that mark these early primates were subtle but revolutionary. A shift from claws to nails might seem trivial, but it reflects a change in how these animals interacted with their environment. Rather than clinging and scratching, nails allowed for more precise grasping of branches and fruits, enhancing manipulation and stability. Forward-facing eyes provided overlapping fields of vision, creating the depth perception necessary for leaping between branches. Enlarged brains relative to body size, while modest compared to later primates, suggest increasing reliance on sensory input and more complex processing of their surroundings. These features were not designed for the ground but for the three-dimensional maze of forests, where falling meant death and survival required agility, precision, and awareness. It is worth remembering that these primates lived in a world still reeling from climatic upheavals. The Paleocene-Eocene thermal maximum, a brief interval of extreme warming about 56 million years ago, transformed forests across the globe. Fossils of primates like Talardina appear almost simultaneously in Europe, Asia, and North America, suggesting that forests stretched in continuous belts across continents, allowing rapid dispersal. This cosmopolitan distribution shows how successful the early primates were at exploiting their niches, but it also reveals how dependent they were on the stability of warm, forested environments. Their very expansion was tied to climate, a vulnerability that would shape their fortunes for millions of years to come. Fossils from this time also reveal something about the social and ecological dynamics of early primates. Tooth wear and isotopic analysis suggest diets varied from insects to fruits to leaves, pointing to niche partitioning even among closely related species. Some adaphiforms likely formed small social groups, as indicated by similarities in tooth morphology across sexes, while others may have lived more solitary lives. Evidence is sparse, and interpretations remain speculative, but what emerges is a picture of animals already experimenting with the ecological strategies that would later make primates one of the most versatile groups of mammals. The importance of the Primate Dawn lies not only in the appearance of familiar traits, but in the pathways it opened. By establishing a foothold in arboreal life, early primates ensured that their descendants would explore a wide range of forms, from lemurs and tarsiers to monkeys and apes. Their success was not inevitable. Many Plesidapiforms and Adapiforms eventually went extinct, but their innovations laid the groundwork for resilience and adaptability. Without those grasping hands, those stereoscopic eyes, and those early leaps into the canopy, the later chapters of primate and human evolution could not have been written. Yet, there is still much we do not know. Many early primate fossils are fragmentary, consisting of jaws, teeth, or partial skeletons. Whole bodies, complete with delicate hands or fragile skulls, are rare, leaving wide gaps in our understanding. Were there other primate-like mammals that thrived in unpreserved regions? How many evolutionary experiments failed, leaving no trace at all? And how much of what we see in today's primates truly began here, in the Eocene forests, as opposed to later stages of their history? These are questions that remind us of the limits of our knowledge and the humility required when reconstructing deep time. As the Eocene forests flourished, primates were there, small and nimble, scurrying through branches and watching the world with forward-facing eyes. They mattered not because they dominated their landscapes, they did not, but because they carried in their anatomy and behaviour the seeds of a lineage that would, tens of millions of years later, ask questions about its own origins. And that is perhaps the most haunting thought, that the story of humanity begins not with dominance, but with fragile survival in the shadows of a greenhouse Earth. What happens when the planet spikes in temperature almost overnight? For most of Earth's history, climate has shifted on slow scales, measured in tens or hundreds of thousands of years. But 56 million years ago, something unusual happened. A rapid injection of carbon into the atmosphere sent global temperatures soaring by somewhere between 5 and 8 degrees Celsius in less than 20,000 years. Geologists call this episode the Paleocene-Eocene thermal maximum, and for the animals alive then it was not an abstract curve on a graph, but a lived crisis. The forests, rivers and seas they inhabited were remade in a geological instant. The evidence for this upheaval is written in sediments, in tiny foraminifera shells from the ocean floor, and in the isotopes locked inside ancient soils. Carbon isotope ratios reveal a massive influx of light carbon, probably from volcanic activity, the destabilization of methane hydrates, or the burning of organic matter. Whatever the source, the effect was unmistakable. A greenhouse world became even hotter, and ecosystems had to adapt, or vanish. At the poles, which had already been ice-free, subtropical conditions extended. Crocodiles and turtles could have basked near what is now the Arctic Ocean. The high latitudes supported forests, not tundra, and those forests became green bridges, linking continents that are today separated by harsh climates. In North America, Europe and Asia, mammalian lineages took advantage of these new connections. Fossil sites from Wyoming to China show sudden appearances of groups such as primates, horses, and artiodactyls within a narrow time window at the start of the thermal maximum. One example is Teilhardina, a tiny lemur-like primate whose remains have been found on 3 continents. Its rapid dispersal suggests that, in this hot interval, forests stretched unbroken across the northern hemisphere, offering routes for migration. What might today seem an impassable Arctic barrier was then a green corridor, but not all the effects were opportunities. For many mammals, the thermal maximum imposed a peculiar pressure. It made them smaller. Fossils of early horses like Cephalhippus show that during this interval their body size shrank dramatically, in some cases by nearly 30%. Teeth and bones reveal animals no larger than a modern house cat, a far cry from the grazing horses we imagine. The The same trend appears in other mammals, including primates. This phenomenon of dwarfing is thought to be linked to temperature stress and limited resources. In hotter conditions, smaller bodies shed heat more efficiently and require less food and water, so natural selection favoured reduced size. It is one of the few times in history when the evolutionary drive was toward becoming tinier, not larger. In the oceans, the picture was even starker. The warmth and acidification devastated benthic foraminifera, tiny single-celled organisms on the seafloor that are key players in marine ecosystems. Up to half of species disappeared during the thermal maximum. Surface waters also changed in composition, affecting plankton communities and rippling upward through food chains. These losses remind us that climate shocks do not just alter where animals live, but can tear at the base of the ecological web. For terrestrial ecosystems, the PETM was a mixed experience. Tropical forests extended into regions that had once been temperate, but they were likely seasonal and drought-prone. In some areas, evidence of soil horizons suggests increased aridity despite overall warming. Mammals had to navigate patchy habitats, with stretches of dense canopy alternating with more open woodland or scrub. These mosaics may have spurred evolutionary experimentation, small primates leaping between branches, ungulate ancestors testing new diets, carnivores probing shifting prey bases. But again, survival hinged on flexibility. Specialists struggled while generalists found ways to persist. The speed of the event is what stands out most starkly. In geological terms, 20,000 years is the blink of an eye. Even recovery, which took on the order of 200,000 years, was abrupt compared to the multi-million-year arcs that usually govern climate and evolution. For us, this has sobering parallels. The rate of carbon released during the PEM, although fast, may have been slower than what we are driving today. If it transformed the planet so profoundly then, we must consider what such a shock does now to systems already strained. One haunting question remains unresolved. What triggered the thermal maximum in the first place? Theories abound. Some point to volcanic outpourings in what is now the North Atlantic, others to destabilize methane frozen beneath the sea, still others to burning peat or soils. It is possible several mechanisms work together, amplifying each other. Our evidence is indirect, filtered through isotopes and sediments. Like detectives working with fragments of a crime scene, we cannot reconstruct the entire sequence with certainty. What we can say is that a sudden pulse of carbon changed the course of life, even if we do not yet know exactly where that pulse began. For mammals, the PEM left a paradoxical legacy. It forced some lineages to shrink and adapt under duress, while at the same time it opened pathways for dispersal and diversification. Many of the groups that define the later Cenozoic, primates, ungulates, carnivores, trace key moments of their early spread to this thermal spike. Without it, their histories, and by extension ours, might have unfolded very differently. The forests that carried them across the Arctic are gone, the tiny horses that scurried in the heat are extinct, but their stories remind us how sensitive life is to sudden climate jolts. We are left with a humbling realization. The Paleocene-Eocene thermal maximum is a window into how fragile ecosystems can be, and how resilient at the same time. It shows us that rapid warming reshapes the rules, leaving no species untouched. And it asks us to imagine, if another spike were to occur, not over 20,000 years, but in mere centuries, what futures would today's mammals face? When did the ancestors of horses, rhinos and cows first appear? The answer lies in a stretch of deep time when the Earth was still blanketed in warm forests, and the world's great grasslands had not yet arrived. Between 50 and 40 million years ago, the hoofed mammals, or ungulates, began to establish themselves as a dominant force. They were not yet the sweeping herds that would one day shape entire ecosystems. Instead, they were small browsers, careful and quiet in the shadows of dense vegetation. But within their skeletons and their teeth, we can trace the earliest hints of what would become some of the most recognizable animals alive today. The ungulates divide into two great branches, and it is here, in the Eocene epoch, that both branches emerge clearly in the fossil record. Perissodactyls, sometimes called the odd-toed ungulates, bore their weight on a central toe, usually with 3 or a single digit on each limb. They would give rise to horses, tapirs and rhinos. Artiodactyls, the even-toed ungulates, balance their weight across two main toes, setting the stage for deer, antelope, camels, pigs, and cattle. This split may sound like a small anatomical curiosity, but it defined entirely different evolutionary strategies. One branch specialized in powerful, often heavy bodies, while the other streamlined itself into efficient runners, and later into the vast herds that came to dominate the open plains. Perissodactyls first appear with delicate creatures like 𝐓𝐈𝐌𝐿𝐼𝐿, once widely known as 𝐓𝐴HIPPUS, the dawn horse. These animals stood little taller than a fox, and did not resemble modern horses except in the most basic outline. With 4 toes on the forelimbs and 3 on the hind, 𝐓𝐴HIPPUS padded through the dense understory of North America and Europe, feeding on leaves and soft shoots. Its teeth were low-crowned, indicating a diet of tender vegetation rather than the abrasive grasses that would come later. Yet its posture and its elongated limbs already hinted at the form that would, through tens of millions of years, stretch into the galloping horse. This was a forest dweller, nimble rather than swift, more a creature of dappled shade than of sunlit plains. Other perissodactyls soon followed. Tapir-like animals browsed in both Asia and North America, their stocky bodies suited for pushing through thickets. These early forms were not far removed from the modern tapirs still living today in South America and Southeast Asia, showing how some lineages preserved their ecological role for tens of millions of years with little need for change. Rhinos, too, began their story in this time. The earliest ancestors, such as 𝐴HIRACHEUS, were light-bodied and small compared with their later kin, but already bore the stout legs and broad grinding teeth that would set their path. They lacked horns, but the skeletal framework of robust skulls was in place, ready for future elaboration. On the other side, the artiodactyls were embarking on a different experiment. One of the earliest and most famous is Diacodexis, a rabbit-sized browser that has been called the first true even-toed ungulate. Its fossils reveal an agile creature with elongated legs and a unique ankle joint, the so-called double pulley astragalus, which allowed for efficient forward and backward motion of the foot. This seemingly small adaptation would become the hallmark of all artiodactyls, from camels to cattle, giving them an extraordinary efficiency for running. At this early stage, though, Diacodexis lived in forests, darting among roots and low shrubs, feeding on leaves, fruits, and perhaps seeds. It was no grazer, but the flexibility in its limb design pointed toward a future in which speed across open terrain would become critical. Artiodactyls quickly diversified. Pig-like and camel-like ancestors began appearing across Eurasia and North America, all modest in size but rich in variety. Their dental adaptations allowed them to experiment with a wide range of plant diets. Some show evidence of omnivory, nipping insects or small vertebrates as opportunities allowed. Others leaned into browsing leaves, their molars developing more elaborate ridges for breaking down fibrous matter. These were small steps, but they marked a turning point. The ungulates were no longer minor forest dwellers. They were diversifying, and in that process they were laying down the roots for dominance in later epochs. What drove this rise? Part of the answer lies in the plants. The Paleocene and Eocene saw the global spread of flowering plants, angiosperms, which created a wide range of new ecological niches. Fruits, seeds, and new types of leaves provided diets that ungulates could exploit with their evolving teeth. Their relatively simple bodies were versatile, capable of adapting without being locked into highly specialized habits. Compared with the more archaic groups of mammals, pantodonts, condylarths, and other odd experiments, the ungulates had flexibility on their side. Another factor was geography. The early Eocene was a warm world, with tropical and subtropical forests stretching far into high latitudes. North America, Europe, and Asia were often connected by land bridges, allowing migrations across entire hemispheres. Fossils of 𝐴HIRACHEUS appear in both Europe and North America, suggesting repeated dispersals across the northern continents. Diacodexis too appears in multiple regions, showing that artiodactyls were also cosmopolitan from the beginning. This constant exchange ensured that innovations spread widely and quickly, reinforcing the success of these groups. It is worth noting that these early ungulates did not yet dominate their ecosystems. They were modest in size, often overshadowed by larger, stranger herbivores, such as winthathers and brontotheres. Yet their potential lay in their adaptability. Where the giants were locked into narrow ecological roles, the ungulates could shift and diversify. When climates changed or vegetation shifted, they could bend without breaking. This quiet resilience would matter more than size in the long run. From a modern perspective, it can be tempting to see 𝐓𝐈𝐌𝐿𝐼 as destined to become the horse, or 𝐓𝐷𝐿𝐼𝐴𝐷𝑒𝑥is as destined to give rise to antelope and cows. But in truth, these were tentative beginnings. Many early ungulate lineages vanished without descendants. For every ancestor that led to modern species, there were side branches that ended in extinction. Fossils reveal a menagerie of now-forgotten hoofed mammals, each an experiment in form and function. Why some survived and others did not is often lost to us. What we can see is that the survivors carried within them the anatomical seeds of future success. By 40 million years ago, the hoofed mammals had secured their place. They were no longer rare curiosities but recurring elements in faunal communities across continents. Still small, still forest-dwelling, they were preparing for the transformations that would come with the cooling climates of the later Eocene and Oligocene. Their story reminds us that evolutionary revolutions are often quiet at first, taking place not with sudden leaps but with subtle shifts that later unfold into dominance. The first horses, rhinos and cows were not majestic herds, but shy browsers in shadowed forests. And yet in those shadows, the foundations of modern ecosystems were being laid. The haunting question is this: how many lineages like 𝐓𝐈𝐿𝐼 or 𝐓𝐷𝐿𝐼𝐴 are we missing from the record? The fossil record is incomplete, biased toward the durable and the fortunate. For every species we uncover, many more must have left no trace. The ungulates we know are but the tip of a much larger iceberg of evolutionary experimentation. Their rise tells us not only about success, but about the countless failures beneath the surface. How did land mammals return to the sea? Around 50 million years ago, in the early to middle Eocene, one lineage of hoofed mammals began a transformation that would end not on land but in oceans. Today, we recognize them as whales, dolphins and porpoises, the cetaceans, but their story began with creatures that still walked on land. Fossils reveal this transition step by step, a rare case where we can trace a grand evolutionary shift not in speculation, but in bones preserved across continents. The first chapter in this return to the water belongs to Pachycetus, discovered in Pakistan. At first glance, it looked like a wolf-sized land mammal, long-limbed and terrestrial. Its skeleton shows it could walk confidently on land, and nothing about its posture suggested an aquatic animal. Yet its skull told a different story. The bones of the ear, especially the thickened involucrum, match those of modern whales and are absent in any other mammals. This single anatomical feature anchored Pachycetus firmly within the cetacean lineage. Though it likely hunted along rivers and coastlines, feeding on fish and small animals, it still looked more like a land predator than a marine mammal. The next step came with Ambulocetus, whose name means the walking whale. Fossils from Pakistan show an animal about 3 meters long, with robust limbs and a long tail. Its body proportions were ungainly on land, but in water they told another story. Its strong hind limbs and flexible spine suggest it swam with a motion like a giant otter or crocodile, pushing itself forward with powerful strokes of its back legs and undulations of its body. The placement of its eyes high on the skull hints that it may have ambushed prey from below, lurking in shallows and then surging upward. On land, it would have moved awkwardly, perhaps dragging itself between waterways, but in water it was at home. As time passed, later archaeocetes became increasingly adapted to aquatic life. Rhodoctus, also from the Eocene of Pakistan, shows shortened limbs compared to its predecessors. Its pelvis was no longer firmly attached to the spine, meaning its back legs could no longer support it well on land. Its long, strong tail likely provided most of its propulsion in water, with limbs acting as stabilizers rather than drivers. Its nostrils had begun to shift upward on the snout, a precursor to the blowholes of modern whales. Each step reinforced the same trend, a terrestrial predator turning into a marine specialist. Then came Basilosaurus, one of the most spectacular early whales. Its fossils appear in North America, Africa and the Middle East, showing how far this lineage had spread by 40 million years ago. Despite its name, which means king lizard, it was no reptile. Stretching up to 18 meters in length, Basilosaurus looked unlike any modern whale. Its body was long and serpentine, with vertebrae elongated into a sinuous frame. It swam not with a vertical tail fluke as modern whales do, but with undulations of its entire body, writhing through the water like an eel. Its skull bore large pointed teeth, suited for seizing fish and other marine animals. Most striking of all, Basilosaurus still had tiny hind limbs, complete with femur, tibia and toes. These legs were far too small to support weight or aid in swimming. Instead, they likely played a role in reproduction, perhaps helping males and females align during mating. They're a fossil reminder that whales began as land mammals, their limbs reduced but not yet erased. These transitional forms tell us that cetaceans did not leap into the ocean fully formed. They passed through awkward, in-between stages, where they were neither fully terrestrial nor fully aquatic. For millions of years they lived dual lives, hunting in rivers and coastal seas, then dragging themselves ashore. Gradually, selection favoured those with stronger tails, better underwater hearing, and reduced dependence on land. By the late Eocene, whales were fully marine. Their legs had shrunk to vestiges, their nostrils had migrated to the top of the head, and their bodies were streamlined for life in water. Why did this transition happen? We can only speculate. Perhaps it began with shoreline hunters like Pachycetes, finding abundant fish and other prey in aquatic environments. The Eocene seas were rich ecosystems teeming with opportunities. Terrestrial competition may also have played a role, pushing some lineages to exploit new niches. Once in water, a new evolutionary pathway opened, with fresh challenges and possibilities. The story of early whales is one of the clearest examples of macroevolution we have. The fossils line up in a sequence, each showing a mixture of old and new traits. It is not a smooth or linear story, but the pattern is undeniable. Land mammals became aquatic predators, and within a span of about 10 million years they had transformed into creatures that never needed to touch land again. It also leaves us with haunting questions. How many intermediate forms have we not yet found? What behaviours did these animals practice that bones cannot show us? Did they live in groups, migrate, or communicate with sound? We can glimpse their skeletons, but the richness of their lives remains beyond us. Still, the bones we do have offer one of the most extraordinary windows into the creativity of evolution. From riverbanks to open oceans, whales remind us that the story of mammals is not one of simple conquest of land, but of constant adaptation to every corner of the Earth. Why did Antarctica freeze, and how did it change mammals forever? Roughly 34 million years ago, the world pivoted. For tens of millions of years, Earth had been locked in a greenhouse climate, warm and humid, its poles forested and ice-free. Mammals thrived in this warmth, experimenting with form and size in jungles that stretched nearly from equator to pole. Then, in what feels like a geological instant, the switch flipped. Ice began to grip Antarctica, the oceans reorganized, and the great Age of Mammals entered an entirely new chapter, the Icehouse World. To understand this change, we must first picture the geography of the late Eocene. Antarctica, still connected to South America and Australia in earlier times, was drifting steadily southward. By the Eocene-Oligocene boundary, plate tectonics had pried it loose. Seaways opened around the continent, most importantly the Drake Passage between South America and Antarctica, and the Tasman Gateway between Antarctica and Australia. This isolation allowed a circumpolar current to form, an unbroken band of water circulating Antarctica, locking its climate into cold seclusion. Without warm tropical currents reaching its shores, Antarctica slipped into a deep freeze. The evidence for this transition lies in tiny shells buried in ocean sediments. Oxygen isotopes preserved in foraminifera record a sudden and dramatic cooling around 34 million years ago. Sea levels dropped as ice sheets formed, and global climates reorganized. Forests retreated, deserts expanded, and the lush Eocene hothouse gave way to cooler, more seasonal worlds. For mammals, this was not merely a change of scenery. It was a filter, extinguishing some of the most successful lineages of the Eocene and opening ecological space for new ones. Among the casualties were many of the archaic herbivores that had dominated earlier epochs. Groups such as Brontotheras, massive relatives of perissodactyls with bizarre forked horns, vanished completely. Their large size and specialized browsing habits left them vulnerable when forests contracted. Similarly, the Litoptons and a range of other South American ungulate experiments suffered major setbacks. Even among carnivores, the once successful creodonts dwindled, unable to adapt to the changing prey base and competition from more flexible true carnivores. In their place, modern mammal orders began to rise. Rodents, already present in small numbers, diversified explosively, their ever-growing in sizes perfect for exploiting harder, tougher vegetation. True perissodactyls such as horses began to elongate limbs and refine teeth, foreshadowing their later dominance on open plains. Artiodactyls too seized the opportunity, spreading into niches that archaic browsers and omnivores left behind. The ancestors of camels, deer and pigs expanded their ranges, often replacing older herbivore groups in the process. One of the most profound changes was the emergence of grass-dominated ecosystems. Grasses had already existed during the Eocene, but under warm, forested conditions they remained minor players. Cooling and drying allowed them to spread across open landscapes. Fossil soils or paleosols from the Oligocene show the first clear evidence of grassland habitats, though patchy and limited compared to later expanses. Mammals responded in kind. Tooth enamel became harder, more resistant to wear. Jaw mechanics shifted toward grinding tougher silica-rich plant matter. Herbivores began to change from forest browsers to grazers, setting in motion the arms race of teeth and grasses that would define much of the later Cenozoic. Predators evolved alongside these new herbivores. The carnivorans, descendants of small Eocene hunters, began to assume the roles once occupied by creodonts. Their teeth specialized for shearing flesh, their bodies streamlined for pursuit. Cats and dogs did not yet exist, but their precursors were already experimenting with forms that would lead in that direction. Flexibility, rather than sheer size, proved the winning strategy. Climate cooling also reshaped migration. With sea levels dropping, new land connections formed, allowing faunal exchanges between continents. Rodents and primates crossed into South America from Africa, forever altering that continent's evolutionary trajectory. In Asia and North America, mammal communities shifted toward more cosmopolitan compositions, with lineages spreading across wider ranges than before. The once isolated ecosystems of the hothouse Earth gave way to a more interconnected biosphere. Perhaps most fascinating is how mammals began to adapt physiologically to seasonality. Fossil evidence of growth rings in teeth and bones suggests that animals faced harsher winters and leaner periods. Seasonal reproduction patterns may have evolved in many groups as a response, concentrating births in favourable times of year. This biological clockwork remains deeply ingrained in mammals today, even in species no longer tied to harsh seasons. What we see in the Eocene-Oligocene transition is not simply extinction but reorganisation. The mammal world pruned away some of its strangest and most spectacular experiments, while laying the groundwork for modern orders. The cooling did not merely change who lived where, it reshaped the very rules of life on land, creating conditions for the ecosystems we still recognise. And yet, the haunting question remains. Why did some lineages vanish while others persisted? Brontotheres were massive and well-established, yet perished. Horses, still small and relatively obscure, endured. Was it diet, behaviour, luck, or a combination we cannot reconstruct? Evolution leaves us patterns, not explanations. What we can say is that 34 million years ago the world shifted into an icehouse state, and mammals that adapted survived. Those that could not became part of the fossil record. How did Proceratherium grow to the size of a small sauropod? In the millions of years after the Eocene gave way to the Oligocene, when Antarctica froze and forests retreated, mammals continued their experiments in form and scale. Among them arose one of the most astonishing land mammals ever to exist, a creature so immense that even today it remains the largest terrestrial mammal known. This was Proceratherium, also called Indricotherium in some literature, a hornless rhinoceros relative that roamed Asia between 34 and 23 million years ago. Unlike many evolutionary giants, it did not represent a side branch of bizarre anatomy. Instead, It was a straightforward herbivore that took the simple rhinoceros plan and stretched it to extraordinary dimensions. Paraceratherium's body mass is estimated at up to 15 or possibly 20 tons, its height at the shoulder around 5 meters, and its head reaching as high as 7 meters when extended. To put this in perspective, an adult could browse at the level of a 2-story building. Its sheer size makes it comparable not to other mammals, but to medium-sized sauropod dinosaurs. Yet despite its immensity, it was not armoured, not horned, and not heavily tusked. It was a giant by scale alone, relying on its massive bulk as protection against predators. No known carnivore of the Oligocene could have threatened an adult Paraceratherium. The fossils of these giants are scattered across Asia, from Pakistan and Kazakhstan to Mongolia and China, telling us they had an enormous range. This distribution reflects the open habitats of the Oligocene. As climates cooled and dried, forests broke apart and patchier woodlands and savanna-like environments appeared. Grasses had begun to spread, though they were not yet the dominant force they would later become. In these settings, Paraceratherium thrived as a high browser, feeding on leaves, soft shoots, and branches far out of reach of other herbivores. Its long neck and massive body allowed it to exploit food sources untouched by competitors. The skeletal anatomy reveals how this lifestyle was supported. The limbs were column-like, similar in design to those of elephants, bearing weight through sheer vertical strength. The skull was long and deep, with a nasal opening set far back, suggesting a long prehensile upper lip or short trunk, useful for stripping foliage. The teeth were simple compared to later grazing rhinos, suited to browsing soft vegetation rather than grinding abrasive grasses. This dental pattern matches the environmental reconstructions. Paraceratherium was not a grazer, but a selective browser, using its height to monopolize high vegetation in semi-open landscapes. What is striking is how this gigantism evolved so soon after the climatic turmoil of the Eocene-Oligocene transition. Many archaic herbivores had vanished in that extinction event, leaving vacant niches. In Asia, perissodactyls, the odd-toed ungulates, were among the groups that rebounded strongly. While horses remained small and tapirs modest, rhinoceratoids surged into larger forms. Some remained medium-sized browsers, while one lineage, the Ungulates, expanded in scale to fill a role once occupied only by dinosaurs. In a sense, gigantism was a recurring solution. Whenever ecosystems stabilized and vegetation was abundant, evolution produced giants to exploit it. But why grow so large? Size brings advantages and costs. For Paraceratherium, gigantism offered access to food unavailable to smaller herbivores, as well as protection from predation. Large size also allowed more efficient digestion of fibrous plant matter, as longer guts could extract more nutrients. Yet such mass required immense daily intake. Estimates suggest these giants may have consumed hundreds of kilograms of vegetation per day, moving constantly across landscapes to meet their needs. Their vast ranges and scattered fossils may reflect this necessity. Populations were sparse, spread thinly across enormous territories to avoid exhausting local resources. Despite their dominance, Paraceratherium and its kin eventually disappeared by the end of the Oligocene and early Miocene. The reasons remain debated. Climate change continued to reshape Asia, with habitats becoming more open and grasses spreading more widely. The low-crowned browsing teeth of Paraceratherium were poorly suited to abrasive grass diets. Competition with other herbivores, including emerging artiodactyls such as early antelope and giraffids, may have intensified. Predation likely played little role, but ecological shifts did. Giants are often vulnerable when environments change, for they cannot adapt as quickly as smaller, more flexible species. The very traits that once made Paraceratherium successful, its size, its specialization as a high browser, may have sealed its fate when ecosystems shifted. Still, its existence remains a landmark in the story of mammals. For a brief stretch of geological time, mammals reached sizes rivaling dinosaurs, showing that under the right conditions, evolution could once again build terrestrial giants. The bones of Paraceratherium remind us of the extraordinary range of forms that mammals have achieved, from shrew-sized insectivores hiding in leaf litter to titans towering over forests. What makes Paraceratherium especially haunting is that we know so little of its behaviour. Did it live in herds, like elephants, or roam more solitarily, like modern rhinos? Did males compete with their massive bodies, or was size alone enough to deter rivals? Fossil evidence rarely preserves these details, leaving us only with scattered bones to reconstruct the life of the largest land mammal to ever walk the earth. Its silence in the fossil record after the Oligocene is equally telling. Giants rise, dominate for a while, and then vanish, leaving smaller, more adaptable creatures to inherit the landscapes. The story of Paraceratherium is therefore not only about scale, but about fragility. Size is impressive, but it is not permanence. Evolution builds giants again and again, but it rarely lets them last. In the history of mammals, Paraceratherium was both a triumph of possibility and a reminder of limitation. It stretched the mammalian body plan as far as it would go and then, like so many giants before it, disappeared into extinction. One of the subtler dimensions of Paraceratherium's story is how it reshaped its environment simply by existing. An animal that tall and that heavy was not just a consumer of plants, but an architect of vegetation. By stripping high branches and pushing through dense stands of trees, it likely altered the structure of forests and woodlands. Much as elephants today open pathways and maintain savanna mosaics by breaking branches and toppling trees, Paraceratherium may have engineered landscapes in ways that allowed smaller herbivores to follow in its wake. Fossil pollen records from Oligocene Asia show shifts between more closed forests and patchier, open woodland. Patterns that could have been influenced not only by climate but by the browsing of giants. Their sheer size also brings into focus questions of reproduction and life history. Large mammals today, from elephants to whales, share certain traits: long gestation periods, slow maturation, and extended lifespans. If Paraceratherium followed this pattern, each calf would have represented a major investment, perhaps born after well over a year of gestation, and dependent on its mother for several years. This slow reproductive pace would have made populations especially vulnerable to environmental stress. A drought lasting just a few years, or a disruption in food availability, could have limited births and tipped numbers toward decline. In this sense, their biology may have tied them to stability more tightly than smaller, faster breeding species. We also cannot ignore the broader faunal context in which Paraceratherium lived. Alongside them roamed early relatives of antelope, camels, and giraffes, many of them still modest in size but already diversifying. Carnivores were present too, though none large enough to threaten a full-grown 𝐓𝐈𝐌𝐿𝐄𝐒𝐒. Instead, predators likely targeted calves, and it is possible that maternal defence, perhaps aided by group living, was an important factor in their survival. The bones of Paraceratherium rarely show clear evidence of predation, but the ecological pressures of raising vulnerable young in landscapes with ambush predators must have been significant. Another underappreciated aspect is their geography. 𝐓�ဣ𝐿𝐄𝐒𝐒 fossils appear across an enormous swath of Asia, yet rarely in dense concentrations. This wide but patchy distribution hints at a way of life tied to constant movement. These were not animals confined to river valleys or forests. They ranged across semi-arid basins, foothills, and seasonal floodplains, moving to follow resources. Their nomadic patterns may have been the only way to sustain such mass, and in doing so they connected ecosystems across great distances, transporting seeds in their dung, and leaving behind trails that other species could exploit. In the end, Paraceratherium's legacy is double-edged. On one hand, it demonstrates that mammals could match the grandeur of dinosaurs in size, reshaping landscapes and standing above all other life around them. On the other, it reminds us of how delicate gigantism can be. The very adaptations that made them unique, immense size, specialized browsing, slow reproduction, also meant that when climates cooled further and competitors diversified, they could not adapt quickly enough. In their bones, we see both the pinnacle of mammalian potential and the precariousness of living too large. Who hunted before lions and tigers existed? Between 30 and 20 million years ago, during the Oligocene and Miocene epochs, carnivorous mammals were already experimenting with the ecological role that cats would later dominate. But the hunters of this age were not the true felids we know today. Instead, they were their precursors and parallels, lineages that evolved cat-like bodies and saber-like teeth long before the arrival of modern lions, tigers, or leopards. These predators, nimravids, and barbarophilids among them, reveal how evolution often repeats its themes, crafting similar designs in different times and lineages when ecological pressures call for them. Nimravids, sometimes referred to as false saber-toothed cats, first appeared in the late Eocene and thrived through the Oligocene. Their fossils have been found across North America, Europe and Asia, showing that they were cosmopolitan hunters in a time when true felids had yet to emerge. Their skeletons show a striking resemblance to modern cats: short, flexible spines, powerful forelimbs, and long tails. Yet their lineage branched off from a common ancestor, with cats well before felids themselves appeared. They were not cats in the strict taxonomic sense, but their convergence in body plan is unmistakable. Some nimravids carried long, flattened upper canines, echoing the saber-toothed condition that would later evolve repeatedly in different groups. Species such as Hoplophoneus of North America display this adaptation, with skulls that suggest they delivered deep, slashing bites to subdue prey. Others had shorter teeth but retained the same muscular builds and stealthy body proportions. Their variety shows that nimravids experimented with multiple hunting strategies, from ambush predators of smaller mammals to takers of larger herbivores in open woodlands. Barbarophilids, often grouped near nimravids but distinct, appeared later, around the Middle Miocene. They are sometimes called bear cats, because of their heavier builds, combining feline-like skulls with more robust postcranial skeletons. Their long saber teeth and deep jaws indicate they were highly specialized killers, adapted to delivering powerful killing bites to large prey. Though not true cats, their ecological role paralleled what felids would later assume. Fossils from Eurasia and North America show that they were widespread and successful for millions of years, dominating carnivore guilds in some regions before fading as true cats and dogs rose to prominence. The repeated appearance of saber teeth across these lineages highlights one of evolution's recurring solutions. Long canines allow predators to kill quickly by slicing through arteries or windpipes, especially effective against large, slow-maturing herbivores. But saber teeth also carried risks. They were fragile compared to conical teeth, prone to breakage, and required precise hunting techniques. Nimravids and barbarophilids, like later saber-toothed cats, may have relied on ambush, powerful forelimbs to hold prey, and swift targeted bites. The strategy worked well in stable ecosystems with abundant large prey, but could collapse when environments shifted. What is perhaps most fascinating is how these predators filled ecological spaces before true felids arrived. During the Oligocene, carnivore communities were diverse and crowded. Creodonts still lingered, though in decline. Early canids and mustelids were experimenting with their own hunting roles. Into this mix, nimravids carved a niche that seemed made for cats, despite not being cats themselves. Their rise shows how ecological opportunities are often seized by whichever lineage happens to evolve the right combination of traits at the right time. By the late Miocene, however, nimravids and barbarophilids began to fade. The reasons are not fully clear. Climatic cooling and the spread of grasslands may have favoured more cursorial predators, those built for pursuit rather than ambush. True felids were by then emerging, armed with retractile claws, refined sensory systems, and flexible hunting strategies. Canids too were diversifying into efficient pack hunters. The heavy saber-toothed forms could not keep pace with these changes. Their extinction illustrates the vulnerability of specialization. Traits that once offered power and advantage could become liabilities when prey species or habitats shifted. For us, the fossils of nimravids and barbarophilids are reminders that what feels unique today may have deep precedents. Cats did not invent the cat-like body, nor were saber-toothed predators a single chapter in prehistory. Instead, mammal evolution shows that certain forms and strategies reappear when conditions are right. Long before lions prowled the savannah, creatures that looked and hunted very much like them already stalked the forests and plains of the Oligocene. Their bones tell us that the role of the stealthy ambush predator is not tied to one lineage, but is a recurring role in the theatre of life. The haunting question is how different the world might look if nimravids or barbarophilids had endured a little longer. Would felids have found their way into dominance regardless, or could one of these parallel lineages have held the role indefinitely? Evolution does not answer such counterfactuals, but the pattern suggests that when one actor leaves the stage, another soon fills the part. Cats before cats remind us that in the deep history of mammals, nothing is inevitable, and even the predators we take for granted are only the latest heirs to ancient roles. Another dimension of the Nimravid and Barbarafelid story lies in how they interacted with the herbivores of their time. The Oligocene and Miocene were full of evolutionary experiments among ungulates. Brontotheres had recently disappeared, Indracotheres towered in Asia, and early artiodactyls and perissodactyls were diversifying into browsers and grazers. For predators, this meant a range of prey sizes, from rabbit-like artiodactyls to rhinoceros-sized browsers. Nimravids seem to have specialised in ambush, waiting in woodlands and forest margins where they could lunge at medium-sized prey. Their forelimb anatomy suggests great strength in grappling, and their claws were likely semi-retractable, useful for pinning struggling victims. Barbaraphelids, with their heavier builds and formidable saber canines, may have targeted larger ungulates, dispatching them with precision, but relying on habitats that allowed for ambush cover. The fossil record also provides glimpses into the social dynamics of these predators, though here we enter into cautious speculation. Most Nimravid fossils are found singly, suggesting solitary habits similar to modern cats. Yet some bone beds contain multiple individuals, raising the possibility of social tolerance, or even group living in certain circumstances. Barbaraphelids, with their bulkier frames, may have required cooperative strategies to subdue larger prey, though we lack clear evidence for pack behaviour. What is clear is that these predators lived in ecosystems where competition was fierce. They were not the only hunters of their time. Early canids, amphicyonids, the so-called bear dogs, and mustelid-like carnivores all pressed into overlapping niches. Survival meant more than power. It meant finding a narrow ecological balance and holding it. Their anatomy hints at the refinements and limits of their strategies. Nimravids had shortened muzzles and expanded areas for jaw muscles, giving them powerful bites but reducing their ability to resist stresses from struggling prey. Barbaraphelids, even more extreme, carried enormous saber teeth that could slice flesh but likely fractured if misused. This delicate balance may explain why these predators were so successful for millions of years, yet so vulnerable when conditions changed. The spread of open grasslands during the later Miocene favoured long-legged, pursuit hunters over ambush specialists. With fewer forests to hide in and prey herds evolving speed as defence, the niche of the saber-toothed ambush hunter narrowed. Paleontologists sometimes describe Nimravids and Barbaraphelids as evolutionary placeholders. They filled roles before true cats were ready to take them, evolving similar adaptations in response to similar pressures. But this description understates their originality. They were not mere prototypes for cats. They were their own flourishing lineages, with unique skull structures, limb proportions and hunting strategies. Their disappearance is not proof of failure but a testament to the unforgiving pace of environmental change. Evolution did not design life with permanence in mind. It improvises, tests and discards, often leaving behind only bones for us to study. It is also worth considering their sensory world. Enlarged eye sockets in many Nimravid skulls suggest strong visual acuity, perhaps adapted for low-light hunting. Their nasal passages were broad, indicating keen senses of smell. Combined with stealthy builds, these features suggest predators that relied on careful approach and explosive short bursts, rather than prolonged chases. Barbaraphelids, with their robust skulls, may have relied even more heavily on smell, ambushing prey in thick vegetation. This sensory ecology offers clues to their lifestyles, but also underlines their dependence on habitats that supported ambush strategies. As grasslands expanded, these specialised senses became less effective compared to the long-distance sight and stamina that pursuit hunters required. In a broader view, Nimravids and Barbaraphelids represent one of the many shadow dynasties in mammal evolution, dominant in their moment, forgotten after their fall. If one were to visit Eurasia 25 million years ago, the most imposing predators encountered would not be cats, but Nimravids, or their kin, waiting in the cover of woodland to strike. Their dominance was real, their presence felt by prey and competitors alike. Yet because they left no living descendants, their story is less familiar than that of lions or wolves. They remind us that the history of mammals is not just the lineage of survivors, but the vast array of alternatives that once seemed permanent. The haunting question is whether their extinction was inevitable once true cats appeared, or whether a shift in climate had already doomed them. If forests had persisted longer, Perhaps nimravids and barbarophilids would have endured, continuing as apex predators in parallel with felids. Instead, their disappearance cleared the stage for modern cats to take the role we now consider natural. It is a sobering reminder that what we see today is not a final product, but a snapshot in a long series of replacements, each predator inheriting a role played many times before. How did grass reshape the course of mammal evolution? Around 20 million years ago in the early Miocene, a quiet revolution began to roll across the continents. It did not arrive as a sudden event, nor as a cataclysm like the one that ended the dinosaurs. Instead, it was a botanical insurgency, spreading through root systems and seed dispersal, slowly remaking landscapes from the ground up. This was the rise of grasslands, and though grasses had existed since the late Cretaceous, it was during the Miocene that they surged into ecological dominance. Their spread altered soils, changed atmospheric chemistry, and most of all, reshaped the teeth, guts, and behaviours of mammals. At first glance, grass seems unremarkable, thin blades carpeting the earth, yet its biology carries subtle weapons. Unlike many plants that invest heavily in woody stems or chemical defences, grasses rely on growth from their base. When grazed, they can regrow rapidly, making them resilient against herbivores. More importantly, their tissues are laced with silica, microscopic particles called phytoliths that grind against enamel like sandpaper. Any mammal feeding regularly on grass quickly wore down its teeth unless it evolved adaptations to counter this challenge. In this arms race between plant and herbivore, teeth became the battlefield. The fossil record documents this transformation clearly. Mammals of the early Miocene still carried low-crowned brachydont teeth, suited for browsing on leaves and soft vegetation. But as grassland spread, lineages began to develop high-crowned hypsodont teeth, capable of withstanding the abrasive diet of gritty, silica-rich blades. Horses show this shift in dramatic fashion. The small, forest-dwelling forms of the Oligocene gave way to larger Miocene species with elongated limbs and teeth that rose high above the gum line, erupting continuously as grinding wore them down. These teeth were evolutionary armour, allowing herds to graze relentlessly without losing the ability to chew. Horses were not alone. Rhinoceroses, antelope, camels, and deer all show similar transitions, with independent origins of hypsodonty across multiple groups. This convergence underscores the scale of the Grassland Revolution. Wherever grasses expanded, herbivores followed suit, adapting their teeth and digestive systems to handle coarse diets. In some, stomach chambers grew more complex, fermenting tough cellulose with microbial help. In others, limb morphology changed, trading flexibility for speed, as open grasslands favoured running from predators rather than hiding in dense vegetation. The rise of grazing herds also altered predator-prey dynamics. Ambush strategies that worked in forests were less effective on open plains. Predators now needed speed and endurance. Canids diversified into pursuit hunters, some resembling the wolves and hyenas of today. Early true cats refined their stealth and sprinting abilities, capable of short, decisive bursts to bring down fleet-footed prey. The grasslands created a new ecological stage, where both herbivores and carnivores became more specialised, and the stakes of survival heightened. Grasslands did more than reshape teeth and legs. They transformed ecosystems from patchy, shaded mosaics into vast, continuous habitats. Herds could migrate seasonally, following rains and regrowth, and in doing so they began to knit landscapes together. Fossil trackways from the Miocene show not solitary browsers but groups of animals moving in unison, evidence of social behaviours emerging alongside open habitats. Group living provided safety in numbers, coordinated defence, and perhaps new forms of communication. In this way, the expansion of grass not only rewired anatomy, but encouraged complex social systems that would define many modern ungulates. Geologically, this transformation is tied to climate. The Miocene saw a gradual cooling trend and a reduction in atmospheric carbon dioxide. These shifts favoured grasses that used a more efficient form of photosynthesis, the C4 pathway, particularly in tropical and subtropical regions. By about 7 million years ago, C4 grasses were spreading rapidly across Africa and Asia. But even earlier, between 20 and 15 million years ago, C3 grasses were already reshaping temperate zones. The soils of these early grasslands preserved dense accumulations of phytoliths, marking their advance. This botanical success came at a cost to other forms of vegetation. Forests retreated, and with them, many browsing mammals declined. Whole lineages of forest specialists either adapted to grassland life or faded into extinction. The Miocene fossil record shows this winnowing clearly. Groups that failed to adapt, such as certain primitive rhinoceratoids and archaic deer-like ungulates, dwindled. Others surged, creating the foundation for modern faunas. The Grassland Revolution was not uniform. In some regions, forests persisted, maintaining refuges for species less suited to open plains. In South America, where grasses spread differently and mammalian herbivores evolved in isolation, unique adaptations arose, distinct from those in Eurasia or North America. The global story of grasses was therefore one of uneven advance, but the trend was unmistakable: a steady reconfiguration of the Earth into landscapes dominated by open, grassy expanses. When we picture the Age of Mammals, it is easy to imagine it always as the world of horses, antelope and cattle-like herds, but those familiar scenes are the outcome of this Miocene revolution, not its starting point. Before grasses spread, mammals lived in forests and woodlands, their diets softer and their movements slower. Afterward, the rules of survival had changed. Teeth had to endure grinding wear, legs had to carry bodies swiftly across miles of open land, and social life became a shield against the dangers of exposure. The haunting question is whether mammals shaped grasslands as much as grasses shaped mammals. Herds grazing continuously may have reinforced the dominance of grasses, preventing trees from reclaiming ground. Predators chasing prey may have maintained the openness of plains by disturbing soils. In this way, the partnership between plant and animal was reciprocal, an ecological feedback loop that locked the world into a new state. Evolution does not move in one direction alone. It is a dialogue, with each participant altering the possibilities of the other. The spread of grasslands also left marks in the microscopic record of mammal life. Teeth from Miocene herbivores preserve characteristic microwear, tiny scratches and pits etched into enamel by the foods they consumed. Browsers that fed on leaves and fruit show rounded pits from softer vegetation, while grazers feeding on grass display long parallel scratches caused by silica grains. These microscopic signatures allow paleontologists to trace the dietary shifts of entire lineages in exquisite detail. In North America, early horses from around 18 million years ago still show browsing patterns, while by 15 million years ago, their microwear shifts dramatically toward grazing. This evidence matches the geologic story of spreading grass-dominated habitats, giving us confidence that the transformation was not just ecological theory, but a lived reality in the teeth of the animals themselves. The soils beneath these grasslands tell another part of the story. Miocene paleosols often contain carbonate nodules, small accumulations of minerals formed in drier, seasonal climates. These nodules, along with grass phytoliths, point to open, semi-arid conditions, a stark contrast to the more uniform, humid forests of the earlier Cenozoic. In some regions, like the Great Plains of North America or the Siwalik deposits of South Asia, layer upon layer of such soils preserve a record of grassland expansion. They show that these landscapes were not static, but dynamic, waxing and waning with climate oscillations, yet trending overall toward openness. Mammals living through this time had to adapt not just once, but repeatedly, adjusting to habitats that were becoming harsher, brighter, and less forgiving of specialization. Predators, too, reveal the subtle impacts of this shift. Fossils of early canids show elongation of limbs and changes in joint structures consistent with running long distances, features less necessary in closed forests. Cats, though still relatively young as a lineage, also began to diversify into forms better suited for grassland ambush, with slender builds and adaptations for sprinting. These morphological shifts are not coincidences. They are the echoes of a world where prey no longer hid easily, and predators had to master either endurance or explosive speed. Perhaps most profound of all is the social dimension. Open landscapes expose animals to constant visual contact with one another and with potential threats. Living in groups became a survival advantage, not only for herbivores but for predators as well. Fossil evidence of large bone beds, containing multiple individuals of the same species, suggests herd behaviour in herbivores and possibly coordinated hunting in carnivores. Though the fossil record cannot show the sounds, signals or bonds that tied these animals together, it hints that the Miocene grasslands were crucibles of social evolution, encouraging cooperation and communication as much as anatomical change. In every layer of evidence, teeth, soils, skeletons, and even trackways, the Grassland Revolution is visible. It was not a sudden conquest, but a creeping, persistent influence, reshaping Earth in ways that still define it today. Grasses are quiet architects, and the mammals of the Miocene were their apprentices, learning new ways to live in an open world. The question that lingers is how many lineages failed this apprenticeship, disappearing into extinction as others mastered the challenge. Evolution's winners are visible on today's plains, but the ghosts of those that faltered remind us that revolutions always come with casualties. Why did apes rise in such dazzling variety during the Miocene, only for most of them to vanish into the paleontological silence? To begin to answer this, we must picture a world between 20 and 10 million years ago, a time often referred to as the Ape Boom. Forests and woodlands spread across Africa, Europe and Asia, punctuated by rivers, lakes and seasonal patches of open land. Into this changing landscape, the ancestors of modern apes expanded into dozens of forms, experimenting with body sizes, diets and locomotion strategies that seem both familiar and alien to us. One of the earliest and most important of these forms was proconsul, discovered in Kenya and dating to around 20 million years ago. Proconsul lacked many of the suspensory adaptations we associate with living apes. It had a flexible spine and limb proportions closer to monkeys, yet its skull, teeth and lack of a tail mark it as undeniably ape. It lived in forests, likely moving on branches in quadrupedal fashion, but its anatomy already hinted at the direction apes were heading: slower reproduction, longer juvenile dependence, and greater investment in individual offspring. These life history traits, while invisible in the bones themselves, are inferred from comparisons with modern primates, and help us understand why apes could carve out ecological spaces distinct from monkeys, even while they shared the same forests. As the Miocene progressed, apes radiated outward from Africa into Eurasia. Fossils of Dryopithecus, found in Europe and dating to around 12 million years ago, show suspensory features: long arms, mobile shoulder joints and curved fingers, suggesting an arboreal lifestyle much closer to modern chimpanzees or orangutans. In Spain, Pierolopithecus exhibits a similar mix of climbing and suspensory adaptations, leading some researchers to argue that it could represent a form near the common ancestor of today's great apes. Yet these reconstructions are debated. The fragmentary nature of many fossils means that each interpretation is provisional, and paleontologists often disagree about whether certain traits evolved once in a shared ancestor or multiple times in parallel. Asia, too, became home to extraordinary apes. 𝐓𝐈𝐿𝐼𝐼, known from Pakistan and India around 12 to 8 million years ago, bore a striking resemblance to modern orangutans. Its facial structure, concave profile, narrow interorbital distance, and tall orbits aligns closely with orangutan features, although its postcranial skeleton suggests less specialization for suspensory behavior. 𝐓𝐈𝐿𝐼𝐼 demonstrates how apes repeatedly evolved combinations of traits that foreshadow modern lineages, though not always in straightforward ways. Alongside it lived another Asian giant, Gigantopithecus, the largest ape ever discovered. Known mostly from teeth and jaw fragments found in China and Southeast Asia, this creature may have stood 3 meters tall and weighed over 500 kilograms. Its molars are massive, with thick enamel suited for grinding tough vegetation. We do not know its full form, but its presence testifies to the extraordinary range of body sizes that apes achieved during this period. Europe hosted its own unique apes as well. Uranopithecus from Greece and Enoiopithecus from Spain highlight the diversity of lineages adapting to Mediterranean environments. These apes show robust jaws and thick enamel, perhaps reflecting diets of harder, more seasonal foods. Their fossils also coincide with environmental changes, as forests gave way to more open woodlands and grasslands. The adaptability of apes to these shifts was both their strength and, paradoxically, their weakness. Unlike monkeys, which reproduced more quickly and thrived in large, flexible groups, apes relied on slower strategies and narrower ecological niches. This tension between flexibility and specialization likely explains why the Miocene ape boom eventually faltered. Around 10 million years ago, climatic cooling and drying accelerated, shrinking tropical forests and expanding open habitats across Eurasia. Many ape species, tied to arboreal lifestyles or restricted diets, dwindled. Monkeys, with their faster reproduction and broader ecological tolerance, began to flourish instead. The fossil record shows a clear contraction of ape diversity in Europe and Asia during this time. By the end of the Miocene, only a handful of lineages remained, ancestors of the great apes and gibbons we know today. The haunting question is why so many forms disappeared, while a few survived. Was it pure ecological luck, or subtle differences in diet and social behaviour that we can only guess at? The bones tell us about locomotion, teeth reveal diets, but the minds and societies of these apes remain elusive. What is clear is that the Miocene was a golden age of experimentation, a time when apes were not a handful of species, but a dominant and varied presence across 3 continents. Their eventual decline reminds us that evolutionary success is not permanent. It is contingent on environments, climates, and chance. We live in a world shaped not only by the survivors, but also by the absence of those lost. In the Miocene forests, the echoes of laughter, cries, and rustles of dozens of ape species would have filled the canopy. Today, only a fraction of that chorus remains. The question that lingers is what the world might have been like if the ape boom had never ended, and whether our own lineage would even exist in such a crowded primate landscape. What do you picture when you hear the word elephant? For most of us, it is a grey giant with tusks, flapping ears, and a flexible trunk, grazing slowly in herds across savannas or forests. Yet the elephants we know today are but a narrow sliver of what once was. Between 20 and 5 million years ago, proboscideans, the broader elephant family, spread across Africa, Eurasia, and eventually the Americas, experimenting with a dizzying array of forms. Some carried multiple pairs of tusks, some bent their jaws in ways that look almost alien, and some reached sizes and shapes we can hardly imagine walking across the earth. It was an age when elephants were not a single image, but a kaleidoscope of possibilities. The story begins with their African roots. By 20 million years ago, the continent hosted early proboscideans that already showed the defining feature of the group: elongated skulls with tusk-like incisors and a developing trunk. From here, they radiated outward, first within Africa and then into Eurasia, carried by shifting climates and newly formed land connections. Their bones and teeth mark them as creatures designed for change, constantly trying new strategies to exploit the resources of their world. Among the strangest of these was Dinotherium. Emerging around 15 million years ago, this genus bore downward curving tusks attached to its lower jaw. At first glance, Dinotherium looks like a creature drawn by a surrealist artist, yet fossils of these animals appear from Africa into Europe and Asia, showing they were both real and widespread. The function of those tusks remains debated. Some suggest they were used for stripping bark, others for pulling branches or digging. Their skulls were massive, their bodies taller than modern elephants, and they walked with the same deliberate gait across Miocene landscapes that were increasingly open, dotted with woodlands rather than dense tropical forests. Their unusual tusks remind us that evolution often takes detours that seem impractical from our modern perspective, yet persisted for millions of years in their own right. Alongside them thrived the Gomphotheres, a group that produced some of the most diverse experiments in elephant history. Many Gomphotheres bore 4 tusks, 2 in the upper jaw, like modern elephants, and 2 more projecting from the lower jaw. Some, such as Platybelodon and Amebelodon, flattened these lower tusks into broad, shovel-like blades, where patterns on their surfaces suggest they used them almost like agricultural tools, slicing through tough aquatic plants or scraping bark. Fossilized pollen and plant remains found in association with Gomphothere sites hint that they often lived in wetlands and floodplains, ecosystems where such adaptations would have been advantageous. Imagine a herd of these shovel-tusked elephants moving through a Miocene marsh, scooping vegetation with their broad lower tusks, while using their trunks to pull in softer shoots. It is a picture at once bizarre and oddly practical. Other 𝐓𝐈𝐿𝐻𝐒s moved in different directions. Some reduced or lost their lower tusks altogether, resembling modern elephants more closely, while still keeping elongated, spiraled or unusually angled upper tusks. They spread widely, reaching North America and later South America, where they would persist until the very end of the Pleistocene. Their adaptability speaks to the evolutionary flexibility of the proboscidean lineage. Where other groups dwindled, 𝐓𝐈𝐿𝐻s seemed to find niches nearly everywhere. Then there were the mastodons, close relatives of true elephants but with their own distinct evolutionary path. Mastodon teeth were built for browsing, with cusps and ridges suited for chewing leaves and twigs rather than grasses. Their fossils are abundant in Miocene and Pliocene forests across Eurasia and North America, suggesting they thrived in woodland habitats where their browsing strategy served them well. Unlike the flatter, grinding teeth of elephants adapted to grasslands, mastodon molars retain a bumpy, primitive appearance, a reminder that there was not a single right way to be an elephant in this age. Proboscidean diversity during this time was astonishing, but it was not without limits. As grasslands spread during the late Miocene and early Pliocene, many browsers struggled. Deinotheris declined as open habitats expanded, their downward tusks perhaps ill-suited for tougher grasses. Some shovel-tusked 𝐓𝐈𝐿𝐻s also disappeared, their specialization locking them into vanishing environments. Others adapted, reshaping their dentition toward tougher diets, foreshadowing the survival of the modern elephant lineages. One of the striking lessons from proboscidean history is that sheer size was not enough to guarantee success. Many of these giants were taller, heavier, or stranger than today's elephants, but the survivors were those that remained flexible in diet and habitat. Modern elephants, whether African or Asian, are the descendants of such adaptable lineages, able to graze, browse, and move across varied terrains. Their long history of experimentation reminds us that the elegant form we recognize today is not inevitable, but the product of countless evolutionary trials, most of which ended in extinction. Standing in a Miocene floodplain, you would not have seen a single kind of elephant, but a community of them. Shovel-tusked diggers, towering deinotheres, mastodon browsers, and forms we still struggle to classify. They shaped ecosystems as profoundly as the great herbivores of the Mesozoic once did, toppling trees, dispersing seeds, and opening paths for other animals. They were engineers of their worlds. Yet when climates shifted and ecosystems transformed, most of these experiments vanished, leaving only a few threads to carry their legacy forward. The haunting question is why, after so many millions of years of experimentation, only a handful of elephant species endure today. Was it simply the relentless narrowing of habitats, the competition with other herbivores, or the chance intersection of climate change and human activity that pruned this lineage so drastically? The fossil record shows us the breadth of their possibilities, but also the fragility of even the mightiest giants. When we look at modern elephants, we're not just seeing survivors, we are seeing the echoes of an entire lost world of tusked forms, each of which once thought itself secure under the Miocene sun. Imagine Africa 10 million years ago. Not the Africa we picture today, of sweeping grasslands and sparse thorn trees, but a continent cloaked in forests, its rivers winding through dense green corridors alive with primates leaping from branch to branch and browsers plucking soft leaves. But this lush world was on the brink of change. By the close of the Miocene, around 5 million years ago, the forest that had once dominated much of the continent gave way to something new. Open savannas, grassy plains that stretched wider with every passing century. The Great Drying reshaped not only landscapes, but entire lineages of mammals, demanding new ways to feed, move, and survive. And it set the stage for one of the most consequential stories in natural history, the eventual emergence of our own lineage. The roots of this transformation lay in planetary forces beyond Africa itself. Around this time, the global climate was cooling and drying, partly due to tectonic shifts. The collision of the Indian subcontinent with Asia raised the Himalayas and the Tibetan Plateau, altering atmospheric circulation patterns. Ocean currents also shifted, particularly with the narrowing of the Tethys Sea and the growing isolation of the Mediterranean. These changes decreased rainfall across large parts of Africa and the tropics, gradually stripping the forest that depended on heavy year-round precipitation. What replaced them was not barren desert, but a mosaic of patchy woodland and open grassland, environments that demanded an entirely new ecological toolkit. For herbivores, the challenge was immediate. Grasses, which had begun their rise millions of years earlier, now expanded dramatically across Africa. Unlike the leafy browse of trees, grasses contained silica, making them far more abrasive to teeth. Animals that once thrived on softer vegetation faced a problem. Their molars wore down too quickly in this new abrasive environment. Fossil records show a striking adaptation: the rise of hypsodonti, or high-crowned teeth, designed to withstand years of grinding tough silica-rich blades of grass. Antelope-like bovids and horse relatives began to diversify rapidly during this time, each experimenting with different strategies for grazing. Some grew broader muzzles to crop large amounts of grass, while others retained narrower snouts to remain selective feeders, focusing on young shoots. The fossil record of African ruminants from this period shows an explosion of forms that mirror the ecological niches seen on today's savannas. For carnivores too, the drying of Africa brought opportunity and danger. In more closed forests, ambush predators thrived, leaping or lunging at prey from cover. But in open grasslands, speed became paramount. Fossils of late Miocene carnivores reveal limb bones better suited for running, with elongated lower legs and lighter frames. Early relatives of modern hyenas, dogs and cats adapted to the chase, honing the endurance and agility needed for life on open plains. Some lineages failed to make the shift and dwindled, but others flourished in the new hunting grounds. Primates, however, faced the most profound test. For millions of years, their evolutionary story had unfolded largely among the trees, where grasping hands, stereoscopic vision, and social behaviours made sense in a three-dimensional canopy. But as woodlands fragmented and open habitats spread, the safety of trees became patchier and less reliable. Fossil evidence from this time hints that some primates began spending more time on the ground, perhaps walking upright for short distances between stands of trees or to forage in the expanding grasslands. These early experiments in terrestrial living foreshadowed the later divergence of hominins, though at this point they were still part of a larger primate mosaic. The question remains unresolved. Did the drying climate directly push our ancestors into new habitats? Or did primates already experimenting with ground life simply thrive when the forests withdrew? The fossil record also suggests shifts in body size among African mammals during this drying period. Many herbivores grew larger, a common trend in open habitats where bigger bodies help conserve heat, travel long distances for water, and deter predators. At the same time, smaller specialists that once thrived in dense canopies found their niches shrinking, and many disappeared from the record. This uneven survival reshaped ecosystems into something resembling the African savannas we know today. Sprawling herds of grazers, pursued by increasingly specialized predators, with primates negotiating both arboreal and terrestrial lives at the margins. We know of these changes not only from bones, but from isotopes preserved in teeth and soils. The chemical signature of carbon isotopes allows us to distinguish between diets based on forest plants and those based on open grass savanna species. Beginning about 7 million years ago, there is a sharp rise in evidence for C4 grasses in the diets of herbivores. This isotopic shift maps neatly onto the spread of open landscapes across Africa and confirms that the Great Drying was not just local, but continent-wide. By 5 million years ago, the transformation was complete. Africa had become a land where grasslands and savannas stretched across vast swathes, punctuated by pockets of woodland and gallery forests along rivers. The mammals that succeeded were those that had embraced the new order: grazers with durable teeth, predators with limbs for pursuit, and primates that were beginning to straddle two worlds, the trees and the ground. It was an ecological turning point, one that both destroyed old ways of life and created new opportunities. The haunting question is whether this was inevitable. Did Africa have to dry, or was it simply the contingent product of shifting plates and changing oceans? And had it remained a continent of forests, what forms of mammalian life might have persisted instead? For us, the drying was destiny, but for countless lineages that vanished in its wake, it was the quiet end of worlds they had once ruled. 5 million years ago, the Earth entered a new act in the story of mammals. The last echoes of the Miocene drying had reshaped continents, pushing forests back and allowing open plains to spread, and into these spaces stepped some of the largest, strangest creatures the world has ever seen. This was the Pliocene, a time before the deep freezes of the ice ages, when global climates were still warmer, sea levels were higher, and ecosystems were thriving with giants. If you had stood on the grasslands of South America, or the plains of Eurasia, or the floodplains of North America, you would have seen landscapes crowded with immense, unfamiliar mammals. The question is, why did so many lineages of mammals grow to extraordinary size in these millions of years? And what role did these giants play in shaping the ecosystems we inherited? South America offers perhaps the most astonishing cast. Isolated from other continents for tens of millions of years, its mammals had taken their own evolutionary paths. Ground sloths were among the most spectacular. Descended from much smaller tree-dwelling ancestors, some grew to sizes rivaling elephants. Megatherium, which lived from about 2.5 million years ago, could reach 6 meters in length and weigh several tons. With massive claws on its forelimbs and a pelvis structured to support upright posture, it likely reared up to strip branches and knock down vegetation, reshaping entire patches of forest with its feeding. Its relatives, like 𝐓𝐈𝐌𝐿𝐿, were equally colossal and spread northward once South America connected with North America. Alongside them trundled glyptodonts, armoured relatives of armadillos, some the size of small cars protected by domes of fused bony plates. These herbivores were not passive background characters. Their bulk and feeding strategies transformed the landscapes they occupied, flattening vegetation, digging for roots, and shaping habitats for smaller species. North America in this period had its own set of giants. Mastodons, relatives of modern elephants, were already present by the Pliocene, browsing on forest vegetation. The continent also hosted immense beavers like Castoroides, nearly as large as modern black bears, capable of reshaping waterways through dam building much like their smaller descendants today. Predators matched this size increase. Saber-toothed cats of the genus Machairodus and later Homotherium stalked the plains, their elongated upper canines perfected for slicing through thick hides and muscle. Fossil assemblages of these predators reveal not only their form but also hints of their social lives. Bone beds of Homotherium suggest group living, perhaps cooperative hunting, a strategy well suited to tackling large herbivores. In Africa, ecosystems were beginning to take on a form that would look familiar today, with herds of antelope, elephants, and giraffes roaming open savannas. Yet even here, the Pliocene giants stood out. Dinotherium, a proboscidean with downward curving tusks attached to its lower jaw, could reach 4 meters at the shoulder. Its unusual tusks remain a mystery. Some propose they were used for stripping bark, others for pulling down branches. Whatever their use, they symbolize the range of experiments proboscideans tried in their long history. Alongside them roamed giant hippopotamuses and massive bovids, while carnivores like Dinophilis, a saber-toothed cat, ambushed prey from cover. Eurasia, stretching across from Spain to China, held perhaps the greatest variety. Gigantic rhinoceroses still lingered, though not as large as the Pariarotherium of earlier epochs. Vast herds of grazing horses and antelopes crossed the steppes. Some primates, too, grew large. Gigantopithecus in Asia, a relative of modern orangutans, reached 3 meters in height and may have weighed more than half a ton, feeding on bamboo and fruit. Fossilized teeth and jaws from China and India hint at its massive presence, though no complete skeleton has ever been found. Its sheer scale shows that primates were not exempt from the pressures favouring gigantism. What ties all of these giants together? Size has evolutionary costs and benefits. Large body mass requires immense amounts of food and water, but it also provides protection against predators, greater tolerance to seasonal shortages, and longer lifespans. In ecosystems with abundant resources and relatively stable climates, natural selection can favour growth to extraordinary dimensions. The Pliocene and early Pleistocene offered such conditions. Expanding grasslands provided vast amounts of forage, and the competition among herbivores may have driven them to grow larger, as both defence and advantage in accessing food. Predators followed suit, evolving forms capable of taking down prey that dwarfed earlier mammals. Paleontologists read these worlds not only from bones but also from footprints, burrows, and isotopic signatures. At Lutoli in Tanzania, for instance, fossilized trackways preserve the passage of early hominins, but in the same sediments are prints of giant proboscidians and other megafauna, showing that these creatures walked the same paths. In South America, burrows large enough for humans to crawl through remain as silent evidence of giant ground sloths that once dug into hillsides for shelter. Each trace speaks to ecosystems where scale itself defined survival. Yet the presence of so many giants raises a haunting question. Why does the Earth not teem with them now? Was this world of giants a stable state, or was it always precarious, dependent on climates that would eventually falter? For now, the Pliocene and early Pleistocene remind us that the Age of Mammals was not simply an age of small survivors growing steadily into familiar forms. It was also an age of excess, of experiment, and of landscapes reshaped by creatures whose size alone made them ecological forces. One of the most revealing aspects of the Megafauna world is how these giants interacted with their environments in ways that still echo today. When a 6-ton ground sloth pulled down trees to feed, it not only nourished itself but also cleared space in the canopy, letting sunlight flood the forest floor. This created microhabitats where grasses and shrubs could thrive, supporting smaller mammals, birds, and insects. In a similar way, herds of mastodons trampled pathways through woodlands, dispersing seeds in their dung and shaping the spread of plants across continents. These animals were ecosystem engineers, sculptors of landscapes whose absence today leaves us with environments that behave differently than they once did. The Pliocene also witnessed astonishing experiments in body form beyond sheer size. In South America, litopterns and notungulates, ungulates, unrelated to horses or cows, expanded into roles filled elsewhere by placentals. Some litopterns evolved long necks reminiscent of giraffes, reaching foliage out of the grasp of smaller browsers. Notungulates explored everything from rabbit-sized forms to massive hippo-like giants. Their diversity reveals how isolation on a continent created evolutionary mosaics that defy easy comparison with modern faunas. Each of these lineages thrived in ecosystems rich with opportunity, filling vacant roles and sometimes converging on familiar forms despite their deep evolutionary distance from them. On the predator side, saber-toothed cats were not the only giants. South America also harboured terror birds, flightless carnivorous birds that stood 3 meters tall. They filled the role of top predators in habitats where large carnivorous mammals were absent, using massive hooked beaks to strike at prey. Their coexistence with saber-toothed cats after the Great American Biotic Interchange shows that ecosystems could support multiple apex hunters, each exploiting different strategies. In Eurasia, hyenas of the genus 𝐓𝐻𝐿𝐿 reached sizes far larger than modern spotted hyenas, with jaws strong enough to crush the long bones of megafauna carcasses. These predators and scavengers highlight how the arms race between herbivores and carnivores extended across continents. What often strikes researchers is how widespread the pattern of gigantism was. It was not confined to a single lineage, region, or climate. Instead, it emerged repeatedly wherever ecological conditions permitted. This convergence suggests that large body size was one of evolution's favoured solutions in the Pliocene and early Pleistocene world. From sloths to beavers, elephants to apes, the same pressures kept nudging mammals toward forms that dominated by sheer scale. It raises a question we cannot fully answer. Was this simply a phase in mammalian history, or the natural endpoint of ecosystems that had matured over tens of millions of years since the dinosaurs' extinction? The evidence left in stone and soil whispers that the world was once tuned to giants, and their shadows still lie beneath our ecosystems. To imagine walking among them is to glimpse an Earth both alien and deeply connected to our own, a reminder that what we see as normal today is only the latest chapter in a far larger story. 2 million years ago, the Earth entered one of its coldest experiments since the extinction of the dinosaurs. Glaciers began to pulse out of the poles, waxing and waning in great cycles that carved valleys, lowered sea levels, and reshaped continents. This was the Ice Age, a time not defined by one unbroken winter but by repeated advances and retreats of ice sheets that could stretch across half of North America and Europe. Into this shifting, unstable world stepped mammals that did not just survive the cold but mastered it, building entire kingdoms of fur, tusk and horn. The question is how so many lineages, from elephants to antelopes, adapted so thoroughly to climates that would have destroyed their ancestors. At the heart of this story are the mammoths. Descendants of earlier proboscideans, mammoths appeared around 2.5 million years ago in Africa, but quickly spread into Eurasia, where they diversified into species adapted to colder environments. The woolly mammoth, Mammuthus primigenius, carried the blueprint for Ice Age survival. Its coat consisted of long, shaggy guard hairs over a dense underwool, while its ears and tail were shortened to minimize heat loss. Even its blood shows adaptation. Preserved genetic material suggests modifications in hemoglobin that allowed oxygen to be carried efficiently at low temperatures. Mammoths lived in large herds across the Mammoth Steppe, a vast biome stretching from Spain across Siberia to Alaska, one of the most productive ecosystems the world has ever known despite its cold. Their role as grazers kept grasslands open, and their dung nourished soil microbes, creating feedback loops that sustained the biome. Alongside mammoths, woolly rhinoceroses roamed the same steppe. Chelodonta antiquitatis grew thick coats and massive horns, which may have been used to clear snow from grasses during long winters. Their fossils, preserved in permafrost and even with intact skin and hair, reveal animals perfectly built for scraping a living from frozen plains. In the same landscapes thrived giant bison, their horns spanning over 2 meters, forming herds that rivaled those of modern plains bison, but at scales adapted to the harsher conditions. Musk oxen, with their compact bodies and luxurious coats, completed the cast of grazers, each species fine-tuned to exploit resources in a world where seasons could turn brutal overnight. Predators were no less remarkable. Cave lions, among the largest cats ever to live, stalked herds across Europe and Asia. Genetic evidence suggests they formed prides, echoing modern African lions, and cave art left by later humans depicts them without manes, perhaps an adaptation to colder climates. Scimitar-toothed cats like Homotherium thrived in both Eurasia and North America, adapted for pursuit hunting rather than ambush, with long limbs and large nasal openings hinting at endurance running in open steppe habitats. Hyenas spread further north than they do today, using bone-crushing jaws to extract every calorie from carcasses. These predators and scavengers formed complex webs around the megafaunal herds, each lineage exploiting a slightly different strategy. Across North America, the story played out in parallel. Columbian mammoths, taller and less shaggy than their woolly relatives, occupied more temperate regions, while mastodons persisted in forested areas, feeding on bark and shrubs. Immense short-faced bears, Arctodus simus, ranged across plains, with long legs suggesting they were adapted for travelling great distances. Some argue they were pursuit hunters, others that they relied on intimidation to drive other predators from their kills. Saber-toothed cats, Smilodon fatalis, occupied ambush roles in woodlands and savannas, their stout builds and massive canines honed for dispatching large prey quickly. The Ice Age did not unfold as one long freeze. Interglacial periods brought warmer conditions, during which forests spread back into higher latitudes. Mammals had to be flexible, tracking shifting habitats. Fossil records from sites like the La Brea tar pits in California show just how dynamic these ecosystems were, with changing species compositions reflecting alternating cold and warm phases. Adaptation to cold was crucial, but so was the ability to migrate and adjust as ice sheets advanced and retreated dozens of times over 2 million years. The persistence of giants during the Ice Age raises questions about energy balance. How could such enormous animals survive in such cold climates, where vegetation was seasonal and growing periods short? The answer lies in the productivity of the Mammoth Steppe. Though frozen in winter, this biome supported dense grasses and herbs during summer months, offering a caloric bounty that sustained large herds. Unlike forests, which lock biomass in trees, the steppe kept its energy close to the ground, accessible to grazers. This ecological richness explains why so many large herbivores coexisted, and why predators could grow to such impressive sizes. It is tempting to see the Ice Age world as alien, but in many ways it was a heightened version of processes we still recognise. Herds of grazers shaped landscapes. Predators adapted to their prey. Climate oscillations forced flexibility. The mammals of the Ice Age were not freaks, but logical products of their environments. The haunting question is whether their grandeur was sustainable, or whether it was always tied to the unstable rhythms of ice. What we know for certain is that the Ice Age kingdom represented one of the pinnacles of mammalian evolution, a world of endurance and adaptation, where cold sculpted life into forms both immense and resilient. 50,000 years ago, the Earth was still very much a kingdom of giants. Mammoths trudged across the frozen grasslands of Siberia. Woolly rhinoceroses scraped through snow to reach tough grasses, and in the Americas, enormous ground sloths pulled down entire trees to feed. Herds of giant bison, antelope, and horses roamed in densities unimaginable today. Predators the size of lions and bears tracked them, some armed with saber-like canines or jaws built for crushing bone. In many places, this was the world our own species walked into, a stage already filled with immense and ancient actors. Yet over the next few tens of thousands of years, the cast of megafauna that had defined the late Cenozoic dwindled. By the dawn of the Holocene, much of it was gone. The haunting question that lingers is why some survived while so many vanished. One explanation lies in the changing climate. The Pleistocene was not a static ice age, but a cycle of glaciations, with ice sheets advancing and retreating dozens of times. Around 20,000 years ago, the last glacial maximum brought extreme cold, but soon after the planet warmed rapidly. Environments that had sustained mammoths and woolly rhinos began to shrink. The mammoth steppe, once stretching across the northern hemisphere, retreated into fragmented patches. Ice melted, sea levels rose, and tundra gave way to forests. Large grazers adapted to open grasslands found their world closing in. For species finely tuned to cold, the sudden warmth was catastrophic. Many could not shift ranges quickly enough, or adapt to new foods as their favoured plants disappeared. But climate alone does not tell the full story. Fossil timelines reveal that extinctions often coincided with the spread of modern humans. In Australia, giant marsupials such as Diprotodon and the enormous predatory lizard Megalania disappeared soon after humans arrived around 50,000 years ago. In the Americas, mammoths, mastodons, and giant ground sloths vanished within a few millennia of human settlement. In Europe and Asia, mammoths survived longer but gradually contracted into refuge such as Wrangel Island in the Arctic Ocean, where small populations persisted until about 4,000 years ago, long after humans had built cities. These patterns suggest that hunting, whether direct or through disruption of breeding cycles and migration routes, played a decisive role. The debate has raged for decades. Was it the warming climate that sealed the fate of these giants, or was it human hunting and habitat alteration? Increasingly, evidence suggests it was not one or the other, but both, working together in a squeeze that left little room for survival. Climate shifts fragmented populations, weakening their numbers, while human pressure pushed them over the edge. In smaller-bodied species, reproduction is rapid enough to withstand losses. But in animals that take years to reach maturity and produce few offspring, even modest hunting could tip the balance. And yet, not all giants disappeared. Elephants in Africa and Asia endured, as did rhinos in limited ranges. Bison survived in North America, though in reduced numbers, and musk oxen persisted in the Arctic. Why these and not others? Geography may have offered refuge. Africa, long home to humans and their ancestors, had megafauna already accustomed to human presence, and perhaps adapted behaviours to coexist. Species there also had wider ecological tolerances, allowing them to adjust to both warm and cold shifts. In contrast, in continents newly reached by humans, animals that had never encountered such predators were more vulnerable. The end of the Ice Age giants reshaped ecosystems in ways we still live with. Without mammoths to keep northern grasslands open, forests encroached. Without ground sloths to disperse giant seeds, many tropical plants lost their partners. The landscape of the Holocene, the epoch we live in, is a diminished echo of what came before. We often think of extinction as something distant and ancient, but in geological terms these losses were almost yesterday. The mammoths that lingered on Wrangel Island lived closer in time to the construction of the Great Pyramid than to the age of dinosaurs. Today, the few survivors remind us of that vanished world. Elephants, rhinos, and bison are not just animals of the present. They're relics of a broader lineage of giants that once shaped Earth's ecosystems. Their struggles against modern threats, habitat loss, poaching, and climate change, mirror the pressures their extinct relatives faced. Their survival is not guaranteed, and in them we glimpse both resilience and fragility. The Age of Mammals didn't end with the megafauna extinctions. It continues, only in a transformed guise. We, Homo sapiens, now stand among the dominant mammals, not by size but by numbers and reach. We have inherited a world that once belonged to mammoths and saber-tooths, and we live with the consequences of their absence. The last question is whether we can learn from that history. Extinction is not only a story of the past, it is a warning for the future. The giants remind us that no lineage is safe forever, and that dominance in one age does not guarantee survival in the next. Thank you, fellow sapiens, for wandering this timeline with me, for drifting into deep time, for slowing down and remembering. If this helped you fall asleep, helped you study, or simply helped you step out of the noise for a while, thank you for being here. If you think more people should know this story, you know what to do. Like, subscribe, share it with the sapiens in your life, and tell me, are you listening before bed, while working, or somewhere in the world I can only imagine? And as always, stay curious, stay calm. I'll see you in the next story.